Here we are. Does everyone see my application and hear me well?
We can hear you.
Very good. Okay, so today, very soon, in about 40 to 50 minutes, I'm very excited to have Prabhakar Ragde give a guest lecture. He's from the University of Waterloo, and I'll give him a proper introduction when it comes time to that. Just before that, I want to motivate this algorithmic idea of type checking. And this is called the bidirectional approach, and explain what connection it has to logic and to verifying theorems, as we discussed last class. I really went quickly in the last 30 minutes, so now let's take some time to go through this and set the stage. So we are working in the implicational fragments, which means that we have logical formulas, these, and right now, the logical formulas are only built from two pieces. They either have propositional variables, which is this variant of the grammar, or they have these, which are implications or arrows. Now, that just defines the grammar of what constitutes a logical formula. So we can have logical formulas like A implies A, or actual A. Propositional variables are any of A, B, or C, etc. They denote logical atoms. Their precise meaning is outside of this language of propositional logic. And just from these variables and using the logical connective of implication, we can form formulas. But that's just a syntactic construction. We haven't specified what they mean yet. For example, in the Boolean interpretation, which gives an idea of truth, the implication A implies A is true. The only time in the Boolean interpretation that an implication would be false would be if there was some assignment of truth values to the propositional variables so that you would have false implies true, which doesn't happen in the case A implies A. But that's from the perspective of truth, which we've put aside. Instead of going through exponentially many verifications of possible ways that we could substitute truth variables, we decided, let's just start with a proof system. Forget about the Boolean interpretation. We're going to define what it means for a formula to be provable. Now, in the course of discussing, well, how do you prove a formula with implications? The way that we did it at the start of the class with informal reasoning was this idea of hypothetical reasoning. You assume something, and then you prove the right-hand side of the implication. When you use this proof tactic of assuming the left-hand side, that was the proof tactic, and it changed the goal of what you were trying to prove. It changed an implication to just the right-hand side of an implication, but you were doing this in a context where you had the left-hand side of the implication as an assumption. And so when we really talk about provability and proof rules, we have to introduce contexts which keep track of the assumptions that we've made. And so then provability becomes this relation. In some context gamma, which consists at the moment of logical formulas, we say that we can prove some logical formula T. So this is our version of a sequence at the moment. Any questions about that?
Just a quick question. What does sequent mean?
Well, I'm not going to give you a much better answer than it means the following thing. It's a type of assertion. It's an assertion that in a context you can prove something. Prabhakar, do you have an answer actually for where the word sequent comes from?
No, I actually don't know where the word comes from, but you can think of it as, as you said, a way of saying something. It's like a logical statement, but it's a logical statement about the system. So it's a metalogical statement.
Right. And the metalogical statement is that in a context gamma, T is provable. That's the meaning of this piece of syntax that's here at the bottom. Right. But as you remember from last class, we're going to modify our sequence, the form of our sequence, when we introduce proof terms, which we'll do momentarily. Then, okay, so when are you allowed to form a valid sequence? Well, those rules of formations of sequence are defined by the following rules of reasoning. If your context has T as an assumption, then you're able to prove T. If in a context that has T as an assumption, you can prove W, then taking T out of the context, you can form an implication. This is precisely the statement of hypothetical reasoning. To prove T implies W, you work in a context in which you've assumed T and you prove W. And this rule is called implication introduction. And finally, how do you use an implication? Well, if you know that T implies W, and here we're working in the same context gamma throughout, and you also in this context know T, then really this context should have a proof for W. This is implication elimination. This is the rule that lets us use implications. Then these three rules inductively define all valid proof trees. And then a sequence is called valid if it is the conclusion of some valid proof tree. So this proof system defines inductively all possible valid sequence, all possible conclusions that you can have at the roots of proof trees constructed through these three rules. Are there any questions? Okay, but that just says, right now, all we've said is, in a context, T is provable. I've said it's provable, but what actually is a proof? And there are several ways to answer that question. One is a very boring way that just goes back to the syntax and says, well, a proof is a valid proof tree with that as its conclusion. Another way to say it, well, another perspective is the BHK interpretation. And in the BHK interpretation, which interprets proofs as programs, the BHK interpretation of a proof of an implication of something of the form A implies B, or rather, these look like propositional variables of T implies W, is some function that takes a proof of T and produces a proof of W. Now, to that end, what do I mean by function? So here we bring in another grammar, and this is the grammar of lambda calculus terms. So a lambda calculus term is one of three possible variants. It's either a variable, and that syntactic category we just denote by this metavariable little x. Although in concrete lambda terms, x would be a reasonable choice to use as a variable. Then the second syntactic category is that of an abstraction. So these are lambdas that take some variable and then have some body which may make reference to that variable. And then the final syntactic category is that of an application, which, when there are rules for evaluation, should be thought of as evaluating a function on an input. But at the moment, we don't have computation and evaluation rules. At the moment, we just have lambda calculus terms, as syntactic entities. And so these three variants, I'll say it again, are called variables, abstractions, and applications. And lambda calculus, created by Church, is supposed to be a pure language of functions and substitution. There's nothing but functions and function evaluation. And to that end, it serves a good purpose for, since also it is established in CS as just the purest form to express functions and evaluation, that's a good model for proof terms. There are functions that take proofs and then do something with them. That motivates us to give a different statement of our three proof rules in our proof systems. We're now going to change the form of a sequence to be annotated with a proof term. So our sequence become as follows. In context gamma, we can prove T, and T, which is some logical formula, has a proof, which is some term T. So this is what our sequence become. And our context also changes. Our context now consists of bindings of variables to formulas. So variable bindings to logical formulas, where the key is that every single term in our context is a variable. And then I'm going to scroll past the original proof rules that we had because I'm about to rewrite them in the new form, where we've annotated the actual theorems, the formulas that we're proving with proof terms. So we're not just saying that T is provable in a context gamma, we're saying more strongly that T is provable and the term T is a proof. And we'll see that this will actually give us a way of reconstructing the proof tree. Because if you just say, this theorem is provable, well, how do you prove it? That's unclear. But if we're actually going to go and assert that, oh, we have a language of proof terms, then just by the conclusion at the bottom of the proof tree, looking at the structure of the proof term, we would hope that that would give us a guide for reconstructing the entire proof tree. So instead of giving you a proof tree in order to show you that I have a proof, I could give you just the conclusion, or more specifically, the proof term. And then sometimes you'd like to prove this in an empty context, and then sometimes in the course of the computation, we'd actually have our context being built up. But either way, our hope would be to produce some algorithm that, just given a sequence annotated with a proof term, would allow us to verify whether that sequence, whether that proof term does indeed constitute a proof of that formula. And so here are our new proof rules. Our first rule about assumption. Now, in the context, let's say x, the variable x, is bound to being a term of type t. Oh, and I'd also want to say another thing. So these are called terms. And in the light of the BHK interpretation, and some things that I suggested before, instead of calling these logical formulas, we can also call these types. And instead of speaking about verifying the proof of a logical formula, we can speak about verifying the type of a term. More on that later. But the language that it's very natural to shift to is the language of speaking about terms and types. So in this case, in context gamma, well, context gamma doesn't necessarily have t, but I've appended to it a proof of t. X is a term of type t. It's a variable, which we assume to have a certain type. Well, anyway, in this context, I can prove t. How do I prove t? What proof will t have?
X.
Yeah, precisely. And this rule right here is now going to be renamed to the more dignified name var, reflecting that the context consists of variables. Next, we have the proof rule for forming implications. So here, suppose that in context gamma, I know that f is a proof of t implies w. Now, f here is a metavariable standing for any lambda calculus term. So it doesn't necessarily have to be a variable. And then suppose also in context gamma, I know that a, again, this is some term, is a proof of t. From those premises, what conclusion should I be able to draw? Also, I suppose this was the third proof rule that we considered before, not the second one.
So the context will be gamma.
Yeah.
That proves W with the proof F of A. Something
Exactly.
like that. Yeah.
And then our final proof rule, which was previously our second rule, is that in context gamma, where I have some variable x of type t, suppose that I have some proof term A, which may have X as a variable inside of it, but on the assumption that X is a term of type T, I can conclude that A has type W. So if that's the premises of our rule, then what conclusion should I be able to draw?
I'm not sure how to write it, but you could say that in the context of gamma, T implies W.
So you're right in that in the context gamma, what we're going to have is a proof of T implies W. But now the way that we've modified our sequence, we're not just going to say that we can prove T implies W. We're more strongly going to say that a certain proof term proves T implies W. And the proof term is going to be some term described by the grammar of lambda calculus that you can see here, which has 3 variants.
Yeah, it's a lambda x on A.
Exactly. And then I write a colon between them. That's what sequence look like. And so the rules, these rules of reasoning for intuitionistic logic with implications, I believe existed before Church's work. And then Church created a system of computation lambda calculus. And by this amazing coincidence, the 3 rules of lambda calculus exactly correspond to the 3 rules of reasoning in this system. And the correspondence is really nice because if you actually look at the conclusion of each of these sequence and you look at the structure of the proof term, in here, the proof term is a variable. In here, the proof term is an application. And in here, the proof term is an abstraction. So if I start with some sequence and I want to construct some tree that has that sequence as its conclusion, then no matter what, if I assume that such a valid tree exists, I know exactly which rule would have been applied just prior to what allowed me to conclude that root, because the 3 variants are mutually exclusive. And so just by looking at which variant it is, you know which rule you will have applied. And this annotation of proof terms is what lets us algorithmically build up a proof tree. Any questions about that? A second perspective, by the way, about what these proof rules mean are just think about it in a programming languages sense, which is distinct from a logic sense. If you have a function that consumes an input of type T and produces an output of type W, and then A is some value of type T, then if you apply F to A, what do you get? You get something of type W. Similarly, if you assume that X has type T, and then X is a variable that may or may not occur in the body of A, but with that assumption that X has type T, you can conclude that A has type W, then what you do is, well, now make X, abstract X away, put X as the parameter of some lambda. Then that function should have type T implies W, or sorry, T to W in that context. Whenever you feed that lambda term something of type T and you substitute it in the body, then A with that substitution made should have type W. And then the first rule is essentially, well, if you have a variable, well, what type does the variable have? Well, a variable doesn't have any other internal structure. So the only way that you can really know something about the type of a variable is if you have an assumption about it. Whereas in the other two cases, whatever term you have has some internal structure. So perhaps if you're discussing the problem about how do I find the type of a term, then they say how that structure could guide. That's the question. So that's one viewpoint from a programming language's perspective, and then there's the other viewpoint from the logic perspective. And from the logic perspective, these rules of reasoning are reasonable. The second one, modus ponens, almost all of Aristotelian logic and syllogisms were just based on repeated uses of implication. Okay, so with these rules being stated like this, and seeing that proof terms look like they might give us an algorithm, because at each step we know what rule we have to apply and we know how the term changes. We set out for the goal of developing an algorithm that would automatically verify a sequence. So that's our goal. Now, before we actually give this algorithm, let's go through an example. So suppose that the sequence that we're looking at is this. So in a completely empty context, I'd like to look at the term lambda A lambda F, and then it takes F and it applies it on A. And I claim that this term has type A to A to B. Well, A implies B implies B in logic. And so I claim that the proposition in logic, A implies B, is a proposition that is provable in an empty context. Provable in an empty context in logic speak is to say that that proposition is a tautology. It holds with no assumptions. Okay, let's say I try and verify this sequence. Then what we said above is that we have three rules, and the three rules correspond to the variance of lambda calculus. And we have a lambda calculus term as our proof term. So by looking at the term, we would know which rule to apply at each step. So then looking back at this, which rule would we apply as the last rule in this proof tree that would allow us to have this as our final conclusion?
Implication introduction?
Yes. So implication introduction is the proof rule that corresponds to abstraction. And you see it on the screen already. And then how would, so I claim that if you just look at the conclusion there, that proof rule has meta variables in it. And then in order to go down to a concrete instance of the proof rule, you have to fill in those meta variables. But just by looking at the conclusion, I claim that all of those metavariables have been filled in. So there's only one way to write what the premises should be. And what is that? So let me ask another question. What is the context gamma? What has gamma been replaced with in here?
Nothing.
Yes. So gamma, the metavariable here, in this concrete instance stands for the empty context. Now, what about A? What term has A been replaced with?
F of A.
But if we look at this, this is lambda. It's an abstraction of something. I guess I can also bracket it. I haven't necessarily introduced strict bracketing conventions yet. So this term is lambda A, and then the body of the lambda is this.
Yeah, that's better. So it'll be the entire thing within the parentheses.
Right.
Lambda and F of A. Yeah.
Right. So that's what the metavariable A has been replaced with. It's been replaced with a concrete lambda term in which F is a variable and A is a variable in this case. Whereas here, A was a metavariable standing for some lambda calculus term. Okay, well, so then the metavariable X ranging over variables has been replaced with what? So what is this X in that term?
Is
In
A.
our term below. Yeah, exactly. Okay, now given those answers, what is the premises? There's only one way to write it. So first off, we're working in a context. What is that context in the premises?
Is the proof A proves the little a proves big A.
Yep, exactly. That's our context. And in that context, something, oh, I need to plug in my tablet in a second, but I'll do this example first. So in that context, some term proves something. What is the term?
It's lambda F dot F of A proves A implies B.
Exactly. Now, looking at this, what rule had to be used again at the conclusion?
Abstraction.
Well, that's the grammar variance. The rule corresponding to that grammar variant is
Implication introduction. Is that right?
and so tell me what's the premises has to be.
The premise is little a proves big A, and there's another one.
Yep.
Would it be little f proves A implies B?
Exactly. I'll leave the parentheses in there. And so those are the two things in our context. And then in that context, a certain proof term proves a certain proposition. What is that proof term?
F of A proves B.
Right, exactly. Now, looking at the proof term, which rule does that lambda calculus variant correspond to?
var. Checking assumption.
Well, if you look at f of a, what type of lambda term is it? What variance is it?
An application.
Exactly. So the rule that corresponds to an application is?
Is it implication elimination?
Good. I probably want to draw this line a bit longer. Okay, and now, so looking at implication elimination, looking at the proof rule here, here. That proof rule has a bunch of meta variables in it. And if you look at the conclusion, those meta variables have been given substitutions. We've substituted lambda terms in for the meta variables to actually get a sequence. So what has gamma been replaced with?
Letter A proves big A, and F proves implies A.
Yeah. And then, well, what has F been replaced with?
Is still F.
Yes.
Oh.
So yeah, the meta variable F got replaced with the variable F. Okay, and then the meta variable A got replaced with the variable A, and the meta variable W, which stands for some type or some logical formula, has been replaced with the logical formula
B.
Okay, what has T been replaced with? Just looking at the conclusion.
It can be anything, like, right?
Yeah, so T does not occur in this conclusion. Notice that there's a lack of T here. So if you just try and say, what has T been replaced with, you can't tell it from this conclusion, which is a bit of an issue. So for example, we know that the rule implication elimination had to be applied if this tree is to be completed, because we look at the proof term and we say, well, what variance introduced that proof term? Well, it was an application. So no matter what, you had to do some implication elimination. Then, well, I know what gamma is. Gamma is in context A. Well, in context A is a proof of A and F is a proof of A implies B. I should have that F is a proof of, and then here's the issue, we don't know what T is. Implies B, which is what W has been replaced with. And then the second premises is again in this context. Oh, and then that has a T again. So we once again have question marks here. Now, so the algorithm of just matching the meta variables sort of gets stuck at the implication elimination rule. This rule is a bit of a problem because T, that meta variable, appears at the top but not at the bottom. But now, just looking at this proof tree, is there a certain privileged thing that we can substitute in place of the question mark?
Maybe
How
capital A.
big A?
Yes. So the question, what goes for the question mark, actually has a definite answer. There is enough information to determine what substitutes for the question mark. But you can't determine that just by matching meta variables. You actually have to determine that by looking at the context. Because what does the context say? The context says that F is a term of type A implies B. And so we're trying to conclude that F has type something, right? And so there is a privileged way to fill it, the question mark in. It's A. This question has a definite answer. And similarly here, there's a privileged way to fill this in, A. Well, after we filled in this A, that determines what T is, and then we can fill in this A without even looking at the context because it has to be filled in there. Okay, well, after we fill in those A's, we're not done yet. We now have two premises and we have to justify both of the premises. Now, looking at the first premises, what lambda calculus variant is F?
A variable?
Exactly. And looking at the variable rule, is this justified? Is the specific rule instance justified from the variable rule?
Yes,
Why?
because it's in the context. What we
Exactly.
get.
Similarly for the second term, right? Why is it justified? Someone else tell me.
Because A is of type capital A also appears in the context.
Right. And so before I said that just looking at the sequence at the bottom, we should be able to construct the proof tree. And then if at every single step we just match meta variables, that works until we get to an application. In this case, we get a bit stuck because we need to find out what T is because T doesn't appear in the conclusion of a rule. And so there, the problem that we're trying to solve changes a bit. Because at every single other step, it was fine. We could just do something. But suddenly, we had to actually fill in a blank. And that's sort of a different computational question. And so that suggests what the process of algorithmically verifying a sequence is. So once again, the goal is to give some algorithm that we can implement in a racket program, in fact, in very few lines in a racket program, that when given a sequence of this form, we'll be able to verify whether that sequence is indeed correct, where the correctness of sequence is defined by these three rules that give an inductive construction of proof trees, and hence also an inductive construction of what conclusions can be at those proof trees. And all of those conclusions precisely define valid sequence according to this proof system, according to this system of inference rules. Any questions? Okay, so what we now see is that perhaps there are two different computational problems at play. The first is you're given a sequence and you want to verify it, right? So the first problem is going to be called type checking. So you are given gamma, the term, and the type, and you want to, and this should succeed, and this will return true if the program can construct a valid proof tree. And otherwise it'll throw an error or fail. Now, one point that I'm not going to discuss right now, but that we're going to come to later, is I wrote it will return true if the program can construct, which is different from writing if there exists. So that's a point that will be addressed later. And then, okay, so the type checking problem is written as follows. We write the sequence that we're trying to verify. Gamma, in context gamma, T is a proof of T. And we write the following symbol. One directional double bodied arrow. So this is how we write the type checking problem. Think about it this way. You can have the term lambda x dot x. And in Racket, we typed this term as A to A. But we equally well could have typed it B to B, or even A to A, that to A to A. In a sense, why did why did we choose A over any other propositional variable? And there isn't really a good reason. But when you're doing type checking, you're checking whether you can force the identity of that type onto the term. Is the term willing to mold itself to the form of the type? The term isn't being allowed to express its own type. It's just saying, can you fit this form? The other problem, which we encountered here when we got to this sequence, for example, is there was a question mark. Now the problem is actually going to be a bit different than what we saw here, because there the question mark was only on the A and not on the implies B. We're just going to replace the entire type with a question mark and call that the problem of type synthesis. So you are given gamma and T, but not T. And you'd like to determine, so the type synthesis, this will return a type, whereas type checking would return true or fail. Type synthesis will return a type or fail. If will return a type if the program can infer a type, if there's sufficient information to infer a type for T. For the program to infer the type of T. And what I suggested before about the identity term, the identity function, being typable as any implication in which the left-hand side is the same as the right-hand side, that sort of idea suggests that really type synthesis should succeed only when there's enough information to infer a unique type. So there's a unique choice of what happens. There's a definite answer. For example, in here, there was a definite answer about how to fill in the question mark because we already had an assumption what f was in our context. So type synthesis will only succeed when there is a definite and unambiguous answer, a unique correct answer to what the type of T, the term T should be. When there is enough information for the program to infer a unique type. Of T, for T, little t. And then this is written as in context gamma, the term T can be synthesized to have type T. Now T is a question mark. So really you should think of the problem instance as being gamma in context gamma, T synthesizes to question mark. It's a computational problem to find out what this actually is. So the problem is only called with these two, but this following sequence written in 3-term form can be read as saying that the type synthesis program returns as opposed to fails, and it returns the type T. So if we think about it as a logical statement about the behavior of two programs that we're about to introduce, then this sequent means that the program inferred the type of T in context gamma returns as opposed to fails and returns the type T. And then here, the logical statement above, and not thinking about it as a call to a program, but thinking about it as logical statements, this sequence then asserts that when we run the type checking program in context gamma on the term T and try and check whether it has type T, then that program returns true as opposed to failing. So that is the meaning of these different sequence when thought of as logically. And then the other perspective is that the sequence are commands to actually run the programs that we're about to describe. So our goal is to write then two functions, a type synthesis function and a type checking function. Why are we writing both of those functions? Well, our original goal was to basically do type checking. And that seems great because we're able to determine what rule that we apply at each step. But we run into a bit of an issue when we get to the implication elimination case, because then there are question marks. And so then we really have a different computational problem in our hands, and that's type synthesis. So in the course of type checking, sometimes synthesis has to happen. And so that motivates the idea that there should be two different computational problems, type checking and type synthesis. And these problems are going to depend on each other. So that motivates that they should exist. I haven't told you how the programs do what they do. I've told you what they should do. Specifically, if the program can check a type, then it returns true, otherwise it fails. And in type synthesis, if the program can infer a unique type, then it returns that type, otherwise it fails. Any questions about that?
Question.
Yep.
So I think I lost like the relation between types and proofs somewhere along the line.
Okay, good question. So there's been an identification of types with logical formulas. So I could say, let's look at the conclusion of this sequence. I could say either that in an empty context, the term lambda A, lambda F, F of A, or I could say the program defined by that term has type A to B to B. Or, so that's the programming perspective. Or I could say it from a logic perspective, which says that the lambda calculus term, lambda A, lambda F, F of A, is a proof of the logical formula A implies B, implies B.
Why though? Like, why is that a proof? I don't know what I'm not following, but
Right. So the motivation that we started off with was, well, we had this collection of proof rules. These proof rules without any terms at the moment, they look like reasonable proof rules for implications, right? And the reason that context had to come in was because we had hypothetical reasoning in our proofs on the first proof assignments. And we saw that when proving hypothetical reasoning, we have to make assumptions. So that motivates context. So if we've agreed that contexts are motivated, then these proof rules seem reasonable. The first one is a basic behavior about actually using assumptions in our context. Then this one just says, this is the rule of hypothetical reasoning, and this lets you use the conclusions that you get from hypothetical reasoning, right?
just the hangman symbol is a state that, right?
Oh, that symbol, by the way, is called a turnstile.
Oh, it's not called the hangman?
Nope. That would be
Really?
like a gamma, I guess. This is a turnstile.
When he
Sorry,
says,
you mean the hangman symbol. Okay, no, that's called a gamma. That is called a gamma. That is a capital gamma.
Oh, I've been calling it hangman for a very long time.
And the key on its side is a turnstile. So context came in because hypothetical reasoning involves hypotheses. And then these three rules seem like very reasonable things for hypothetical reasoning. Now, I haven't yet connected what the idea of context is to the Boolean interpretation. We can do that later. But after that's established, you can also check that the three rules fly with the Boolean interpretation.
So the turnstile is assert that.
So the sequence together says in context gamma T is provable.
In context, gamma T is provable. And so the assertion is that, oh, okay, so when you have T in your context and T is provable, okay, fine. Oh, I see, okay, I see what I was missing. But then, okay, so how's, like, how is, again, so now that I get that, where does the type to program connection come in again?
Right. So the statement that some logical formula is provable isn't that strong of a statement. More specifically, you'd like to actually say, well, not only is it provable, like I can say it's provable. That's good, but how do you actually know that I'm being honest? How do you know that it's provable? Well, okay, you can give a proof tree, but let's have that actually the entire proof tree encoded in the sequence itself. So not only can we say that in context gamma T is provable, but we in fact say that in context gamma, the following syntactic expression is a proof of T.
Okay.
And now, how is that motivated? Well, think about proving an implication. In an implication, you make an assumption and then you use the assumption somewhere. How do you use an assumption? Well, if you have a proof of the thing that you're assuming, then you can substitute it in. And that's a computation. So that's from the BHK interpretation, which interprets proofs as programs. The idea is that a proof of an implication should be a lambda, which is just a machine for when it's actually evaluated on something, causing a substitution in the body of T for of the argument for X. Then Alfonso Church has this language of lambda calculus. Now, what connection does lambda calculus have to proofs here? Why should they have any connection at all? And then all that we did is we took the proof rules that we had before and we added proof terms to them. So for example, if you looked at any proof tree using these proof rules and then you just erased all of the proof terms, you'd get a proof tree in the original system without these terms, without the terms, right?
Can you repeat that? Can you repeat that? The last sentence.
So let's look at this proof tree that we had actually here. Take all of the proof terms, take all of the lambda calculus terms and colons and delete them. If you do that, then you have a valid proof tree for our original version of sequence, which didn't have proof terms. Then you have a proof that in an empty context, the formula A implies B implies B is provable.
A implies B is provable.
So you get that assertion by removing the stronger assertion that the term is a proof of it.
I don't like. Well, A implies B implies B, right? Like if why wouldn't you just make like a truth table? I don't understand.
So because we're making a difference between truth and proof, we would like to discuss proof systems, not truth systems. Right now, there's no discussion of truth. We want to discuss, so for example, a proof, if you verify that this tree correctly follows the rules of reasoning, then that is a short certificate of the correctness of the statements. You can imagine statements that have 10 propositional variables, but that still have short proofs. Now, no matter what, if you were doing a truth table with 10 propositional variables, you'd have to go for an exponential count. But that's not the only reason. It's not only practically motivated. There's also a deep reason for why the notions of truth and proof should be kept separate. And hopefully everything that we do in this class will provide a compelling argument for that.
So the proof tree, you have your when you're doing these, like the process of reasoning, essentially you have implication and you have like substitution and
well, we're not actually doing computation yet. So here, I can undo things. So let me cross out all of the proof terms here. So if I cross out the proof terms, then what I have here now, if you ignore that, is a proof tree for the sequence. In an empty context, that logical formula is provable. And that sequence it's a proof tree that is constructed using these 3 inductive rules of reasoning.
Which is, yeah, I mean, T implies W, and you have T, then you get W, fine. Okay, well, can you go back to the proof again? Like,
yes, so now that I've crossed it out, all of the proof terms, I now have a proof tree that shows that that is provable.
Oh, well,
now I'm going to uncross out the proof terms.
I don't see how you have that though, because like you have A implies B. What's the question mark supposed to be saying?
Oh, so that was, ignore the question mark for the moment. The question mark was the question of, I'll get to that in a second. So if you ignore the question mark and you see an A there and you imagine everything that I've crossed out, you do get a syntactically valid proof tree using the rules that I showed you above. Do you agree with that statement?
Can you write it on the side? Because I think all the symbols are just making, I can't really read this.
Okay, I can show you what's, I won't write the entire thing, but I'll write part of it. So the thing at the bottom would be the sequence. In an empty context, you have, it's possible to prove A implies B, implies B. Sorry, implies B, yeah. So that would be the proof rule that I'd have at the bottom of the tree.
Okay.
Now it's not annotated at all. Now it's just the sequence. Well, that follows from something, right?
Yeah.
what does it follow from? It follows from if I've assumed A, if in the context in which I have A as an assumption, I can prove A implies, well, it's possible, A implies B is provable. If in the context A, that logical formula is provable, then it should also be true that in the empty context, this new formula formed from implication is provable, right? Okay, and then I go one step above. Then the next line would be in the context where I have two assumptions, not only A, but also A implies B. Well, from those assumptions, if it's true that B is provable, then it should also be true that that formula formed from implication is provable with one less assumption, right?
Yeah, okay. So this is like a different way of writing like the general way it's done in like logic, where you have like, you know, the MP and the rules on the side. Okay.
Yes, exactly. But here's the thing. And this is where we depart from standard Math 250 material. We're not satisfied with the statement that something is provable. We'd actually like to make a stronger assertion that a certain term encodes the proof. So not only are we going to go ahead.
Like, how is that assertion stronger? Like, I actually don't get the assertion itself.
The assertion that T is provable is the same as saying there is some proof term, so that the second sequent is valid.
Right. Oh, okay.
Here, I'm not just telling you that T is provable. I'm actually giving you a proof. And the proof is going to be a lambda term. Now, why does that constitute a proof? That's a question. That's a very good question to ask. Why does a lambda term constitute a proof? And the claim is that given a lambda term, you can algorithmically construct a proof tree. Now, why
isn't that what we just did?
That's what we're doing right now, exactly.
No. Isn't that what the thing we just did with the assuming the context?
Oh,
you know, and
well, okay. What rule of reasoning do I use next? Here.
Where?
Here. Let's say I'm building this up right here. What rule do I use next?
Well, A implies B, then B. Well, you have A, and then you can just, you know, do modus ponens, and you get, well, B.
Yes, but you can't tell that just from the form. You actually had to decide which rule you were using, right? What if B was in the context?
What if B was in the context? Well, then you just use direct, well, what's the,
right,
I don't know the word.
But you actually have to determine which one of those two cases it was, right? Now, yeah. I can show you something even more complicated. There's a third option that you could do. You could claim, for example, you can try and prove that A implies A, and then you can use the assumption A to conclude A. So you can do a lot of wasted computation. There isn't a unique option from what to do. So for example, you can try and prove that, you can try and get the conclusion A by proving A implies A and then showing that since you have A, using modus ponens on that.
Wait,
so
you're telling me that there's a way you can take any like sequence of like logical connectives, look at it and say, and like letters, and look at it and like show uniquely that there is like a simple, like there's a simplest way of solving it, like down to.
Oh, well, that's a completely different question. That's a question of normal forms for proofs, and that's something we might come to at the end of the class. But I am telling you that if something is provable, there are lots of incredibly wasteful ways to go about it. So yeah. I can write an arbitrarily long proof tree for this. But what I'm saying here is that a lambda term does not just say that something is provable. A lambda term encodes a proof tree. The entire proof tree, the information of everything that I write in the proof tree should be contained in this term.
Oh, Okay, so how does that do it here? Like over here, you have like lambda A and lambda
Right.
F.
So
FA.
first off, why does it do it at all abstractly? The first reason is because there are 3 grammar rules in lambda calculus: variables, abstractions, and applications, right? And if you look at the 3 rules of reasoning, then the proof terms on the conclusion, each one of them corresponds to a unique grammar variance.
What's a unique grammar variant?
Okay, so if you have a lambda term, it is either a variable or an abstraction or an application.
Yeah.
And it's impossible to get confused between the 3 of them.
Uh-huh.
Now, in your context, when we made sequence happen, the contexts have variables annotated with logical formulas or variables annotated with types. So if you look at the 3 rules now, and you look at the things that I've underlined in green, each one of those is a different lambda calculus variant.
Yes. So like.
So in other words, if you just have the conclusion, then you know for a fact that if there is a valid proof tree with that conclusion, then the last rule that had to be applied had to be that specific one.
So if you're going to apply an implication, which is basically a substitution, then you have your
But there's no
abstraction.
implication. Implication is a construction in logical terms. There are only 2 variants for terms. For formulas. What we're going to do is that our program for verifying a sequence algorithmically is going to be structurally recursive on the proof term, not on the logical formula. So it's not an implication. Okay. So there are. How do you prove an implication?
You
let's say
assume the antecedent and then you show the consequence.
Not necessarily. Suppose that you have A implies B as an assumption.
Okay.
And suppose that you also have A as an assumption, right?
Yeah.
Then you can prove A implies B by using modus ponens.
Yes.
So that's a proof of an implication that does not use hypothetical reasoning. You've concluded an implication with implication elimination, not implication introduction.
Oh, okay.
So in other words, there are only 2 variants in the grammar of terms, whereas there are 3 variants, whereas there are 3 rules. So just given the structure of the logical formula that you want to apply, it's not clear what rule you want to use. Whereas if you look at the proof term, it is unambiguous which proof term that you want to use, which rule you want to use, because each rule corresponds to a unique variance in the grammar of terms.
Unique variants in the grammar of terms, which are the 3, right? So you have the variable, which is just a variable. And what is a T?
T is a metavariable standing for any logical formula.
So
look at the top. Before, we have this grammar right here. We have this grammar of logical formulas. Capital T, this syntactic category, is either a propositional variable, capital X, or an implication. That's a grammar, right?
Yeah, it's either a, yeah, okay.
And then here's the grammar for proof terms, right? So our sequence are always of the form some context gamma, where gamma is a collection of things that look like this.
Mm-hmm.
And then you have a lambda calculus term, colon, a logical formula.
You have a lambda calculus term, colon, a logical formula. Wait, where's the lambda calculus? Okay, so you have a lambda calculus term, colon, a logical formula, and the lambda calculus term explains the logical formula?
Well, so the meaning of the sequent is that lambda calculus term is a proof of that logical formula.
Yeah, a lambda calculus term is a proof of that logical formula.
Yes. So now look at the rules of reasoning that we have. The entire system is defined by these 3 rules.
Oh, and if your logical formula is just a variable, then like I suppose you just have to.
Your logical formula is never is never a lambda calculus variable. Your logical formula is a propositional variable or an implication, but your lambda calculus term might be a variable. That's the important one, not the formula. You're not looking at the structure of a formula.
So
You're looking at the structure of the term.
If your propositional formula is A, what's the proof for that?
You don't know. I'm not say the rules don't say. If you look at the proof term. So remember, before we were discussing here, we were discussing that if you don't have proof terms, you can make very big proof trees that are inefficient.
Yes.
But it's the proof term, not the logical formula, that encodes a unique tree.
So like, I don't understand why this question doesn't have an answer. If you have like if you A is a logical formula. No, not a logical, a propositional formula, right? Like A, just A, capital A.
Yes.
Does it have a proof or not?
Oh, well, in the empty context, it does not have a proof.
Only if there's like an A in the context will it have a proof, right?
No, you don't have to have an A in the context. You can also have a B implies A in the context and an A in the context.
But then you'd also need a B.
Oh, sorry, and a B in the context.
Okay.
But you don't know what rule you use to conclude A. It could either.
The proof term takes you from the context to the logical formula.
The proof term encodes a proof tree. The proof term is supposed to have all of the information of this proof tree.
So the proof term, like given a gamma, the proof term will give you a proof tree for the propositional formula.
Yes, that's precisely what our goal is. Our goal is to give an algorithm that does that.
And then we encode that algorithm in like lambda calculus terms using these three things.
The algorithm is going to be structurally recursive on the lambda calculus term.
The algorithm is going to be structurally recursive on the lambda calculus term. So if I like write down like lambda calculus terms, like if I take these three things and I make like a thing, it can always be parsed into a proof tree using this algorithm.
If it's valid.
If it's valid. And if it's not valid, then it means that there's no proof.
Let's leave that point for the moment. So that's a separate question. We're going to say for sure if the program accepts the proof, then it's provable, right?
Oh, is this where the halting problem stuff comes in?
So it doesn't have to here, but it can come in later. It's at some points the question might become uncomputable. But that's a separate, very complicated question, right? So let's not talk about that right now. Also, I want Prabhakar to actually talk at a certain time. So
thank you. Like I got it.
But I think your questions are good. Your questions are clarified the main point here, right? But you get the main point now?
Yes.
I mean, the main point is you're given a sequence that says that some lambda calculus term is actually a proof of your logical formula. And that it's a proof really means that there should be some algorithms that construct a proof tree from that proof term. And so here we did this example live. We started the sequence at the bottom and we said, let's try and construct a proof tree, right? And then it was good, smooth, easy flowing until we finally got to a point at which we used the implication elimination rule, and then we didn't know what T was. And so really that suggests that there are two problems going on. One is the type checking problem, where you're trying to verify the validity of a sequence. And one is a type synthesis problem, where you're only given a context and a term, and you're trying to, from that, infer whether there's a unique type which fits the term. Oh, let's see. Prabhakar, should I go through the bidirectional rules, or now that I've motivated the problem, would you like to talk? Because
no, I think it might make sense for me to do that because they're on my slides. So
right,
I can do that.
Perfect. So I'll take any more questions, and then I'll let Prabhakar take over. And I'll also give him an introduction. But first, any questions?
Yeah. So given a logical formula, how do you know what lambda calculus term encodes a proof of it?
So here's the thing. Remember the Boolean interpretation where you just had to check all of the possibly many exponential options, right?
Yeah, using a truth table.
So a computer is always able to, I mean, it might be incredibly inefficient, check all of the options, right? So there, the proof of truth is sort of, it's exponentially large. No matter what, in order to convince someone, you have to go through an exponentially large proof. Whereas here, the idea is that you have a very small proof that out of all of those exponential options just eliminates them and has this, it's a small certificate that you can check. But because it's a small certificate, it means that finding it is hard. Right. So that's the problem. Instead of just doing a brute force, completely unintelligent search through a logical table, you're cleverly giving a proof term that does exactly the right thing. And that's, well, in math, you don't just algorithmically prove things. You actually have to find what the proof term is. And Prabhakar will actually show a proof assistant, and the proof assistant will have an interactive element which helps you develop what the proof term should be.
Cool, thanks.
Anyone else? Okay, so I guess the last thing that I'll say material-wise is just keep in mind, remember that there are two algorithmic problems going on, type checking and type synthesis. And the notations for them are these arrow notations. Here you have the type T and you're trying to force it on the term and trying to see whether the term will accept it. And here, out of the term, you're trying to squeeze what the type is. Okay, and now I'll do the introduction. So we're very fortunate to have Prabhakar Ragde. He's a professor at the University of Waterloo. A long time ago, he was in the algorithms group, but as of late, he's been in the programming languages group. Now, apart from research on programming languages, Prabhakar Ragde has played an instrumental role in developing the CS curriculum of the University of Waterloo. So for example, he was a key figure in the university switching to Scheme for all math faculty classes. And after also developing the standard courses, he developed advanced offerings of those courses. He has a serial habit of going through certain course materials and finding completely novel ways for presenting them. So I think there's at least 4 courses that you've designed, right?
Yeah, at least, yeah.
And he's a brilliant presenter, and hopefully that's something that you're going to see. So this should be a very good treat. I'm now going to stop screen sharing and let you take over from there. Oh, perhaps do we want to take a 3-minute break so that afterwards we can give Prabhakar full attention? I think that might be a good idea.
Yeah, sure, let's do that.
Yes, so let's start at 3. Just a quick break. Right. You can start sharing for the moment.
Okay.
I think we can take it from here.
Okay, you want me to start? Am I audible?
Yes, you are.
All right, so thank you, Taras, for inviting me here, and thank you for that generous introduction. I hope I'm up to it. So for those of you in Math 250, I wanted to start by stepping back a little bit and saying, well, Taras has been throwing a lot of stuff at you. Where is this all coming from? So let me give you a little bit of context here. So Taras is synthesizing this course from a whole bunch of sources. And some of them are not listed here. Like clearly, history and philosophy of mathematics plays a big role in his thinking. But I want to highlight 3 particular sources because they lead us towards what you're going to be doing in the last 2 weeks of the course. By the way, I have to sort of apologize for a few things here. I'm in a 2nd bedroom, and the landlord has painted it dark teal, and I don't know why. And the lighting sucks, but hopefully you're not here to see my face, so it's not a big deal. Also, this is the first time I'm presenting over Zoom. I wasn't teaching when COVID hit. And in fact, although I'll be teaching this fall, there's not going to be any synchronous lectures. It's all going to be asynchronous. So this is the one time I get to try to do that. So if you'd help me out by asking questions, please, anytime I'm not clear, that will help a great deal. Okay, so as Taras mentioned, I teach at the University of Waterloo in Canada, although right now I'm in Brooklyn. So I know you're maybe not physically at Stony Brook, but if you're on Long Island, well, so am I. So the University of Waterloo has a faculty of mathematics, which is large. We have 250 full-time faculty members. There are several departments, including pure math, applied math, and computer science is also one of the departments in the faculty of math. So there's a math core. Students take several math courses, and all of them have to take 2 computer science courses. So when Taras came into the University of Waterloo at your age, he took an advanced math course, which is kind of like what Math 250 would be like if you were taking it from any other instructor. The Math 250, the conventional Math 250 is kind of in between the advanced math course at Waterloo and the regular math course at Waterloo. But Taras also had the option of taking an advanced computer science course. So we get about 1,500 undergraduates starting every year, and about 100 of them take the advanced math course. Maybe more now that there's 2 sections. And about 100 of them take the advanced computer science course. And there's a fair amount of overlap because advanced, in the way I designed the course, advanced computer science didn't mean prior experience in computer science. It meant enthusiasm for the subject or willingness to be enthusiastic and aptitude in mathematics. So we get good math students, and I wanted to give them a good exposure to computer science. So that was the course CS 145, and Taras took that along with his advanced math course. And in that course, he saw some things that he later showed you in your first lecture in Math 250. The definition of NAT using S and Z, the definition of plus, the proof that 0 is the identity for plus. These things were all present in my first lecture. And some other things, right? We go on in CS 145 to learn about racket and to see things like structures and lists and higher order functions. All these things are in CS 145. So why, what does this have to do with Math 250? So let's continue with the sources. Another one of Taras's sources is another computer science course, which he encountered not at Waterloo, but at Stony Brook. It's CSE 526 at Stony Brook. It's a graduate course called Principles of Programming Languages. And although he didn't take that material from me, I teach a course with the same name at Waterloo. It's a 4th year undergraduate course, cross-listed as a graduate course. And both of those courses use the same textbook. It's kind of a standard textbook for this work. It's called Types in Programming Languages by Benjamin Pierce, who's at the University of Pennsylvania. A very good book. So, and from that book are things that you have seen, for example, the if expressions, the idea of rules for stepping through things, the congruence rules that let you go in and rewrite a subterm. All of that stuff is from Pierce's book. And in fact, the material you saw late yesterday and early today is essentially the simply typed lambda calculus, which is in chapter something like 9 of Pierce. And the material you just started to see about type checking and type synthesis comes out of the implementation of type checking, which is chapter 10 of Pierce. So all of this material is preparatory for what is happening in the second half of the course, which is that you're going to start seeing how to express logic in terms of, in active terms, in constructive terms, in terms of programming. A proof is not just something that sits on the page. A proof is something that accomplishes something. It has an action, which is kind of an interesting way of thinking about it. And if you look at the bottom of the slide, it sort of explains some of the reasoning behind going this route. And on the very bottom line, I talk about informal computation versus formal computation. Taras has already talked about informal math as being all the math you've seen up to this point, and formal math or logic as the stuff that you're now seeing. And in the same way, you can talk about informal versus formal computation. I know that, so I haven't been lurking in real time on your lectures, but I have skimmed through them, the recordings. And I know that some of you have asked questions that indicate that some of you have seen computation before. Maybe in high school you learned Java or Python. And you probably learned it in what I would say was an informal way, which was, here's a new feature. Here are 3 or 4 examples. Now you know it. Let's go on to the next feature. Here are 3 or 4 examples. Now you know it. You do a lot of learning this way early in your life, learning through examples. And you can do that too for simple concepts. But as things get more and more complicated, you have to start shifting towards being more formal. For writing down the rules, and then examples are to illustrate how the rules work. And that sort of movement from informal to formal is what you're seeing in this course. And it's part of your evolution as mathematicians, really. So I taught this course using Pierce's book, and I'm teaching it to 4th-year computer science students. So they've had all those math courses, and they've had courses in computer science, including algorithms and data structures. They know a lot. And yet, when they were asked to do things that you have seen, so things like the if expressions, you can always, when you reduce them down to a value, that process terminates. And you can prove that. And when I asked them to do proofs, they had trouble with the proofs. They struggled with the proofs. Now, I saw that in CS 145 as well. So some of the proofs that Taras had you do, proving that add and plus are the same thing, I asked him to do that at some point, and it's difficult, and it's not easy. And I realized that when I see what these really good math students we get at Waterloo, how they dealt with these issues. They faced the same issues that you faced in doing your homework. And I started to realize, well, yeah, something is missing. What is missing here? The problem is that for all is really trickier than it looks. And I thought maybe I should put off doing that, asking people to do proofs until maybe after Lambda, because Lambda illustrates some of the ideas of for all, and maybe that will work. But then when these senior students were running into the problem, I thought, okay, there's something deeper here. Something is going on. So Pierce felt that, I think, too, at the University of Pennsylvania, because he embarked on a multi-year project to redo the ideas of types and programming languages, but using a piece of software, a proof assistant. So the proof assistant would help students to write the proofs, and you would actually, what Pierce would actually do was create models of programming languages and then prove things about them with this proof assistant. That work is available online. It's a free online textbook resource called Software Foundations, and it's really quite nice. It uses a proof assistant called COQ. And I taught a graduate course using this, and it was a success. I taught it again. Students really liked it. And part of what they really liked was that this proof assistant was fun. It was kind of like a game. It got really enjoyable. And so they actually looked forward to their homework. But they would ask me questions and they'd say, well, what is the proof assistant doing here at this point? And sometimes I could answer them because I learned about what was going on underneath the surface. But sometimes I couldn't. And what I did was, well, I had Racket, which was what got me into programming languages in the first place. And I decided to use Racket in 145 for a couple of reasons. One is that it's really simple compared to the informal computation. You know, languages like Python and Java, there's a lot going on there. There's a lot to learn. You have to spend the whole first course learning how to program with no content. But there's not much to Racket. There's not much there. And with that little bit of powerful stuff, you can do a lot. So you can learn Racket quickly and then start to see some serious content, some algorithms and data structures. That was one reason that Racket was good in 145. The other reason was that it's moving towards formal computation. You don't have to present it by examples. You can present it by rewrite rules, and the rewrite rules are just algebraic substitution, which you learned in high school. So the computational model is one that you're already familiar with, and it helps you understand when your programs are wrong, the difference between what you thought you were doing and what you actually did in the program. And you don't have that with Java. When your Java program goes wrong, it's because you went too far from the example you saw, and you don't know what, you know, you're in unknown territory. You don't have a mental model. Racket, you can and should get a mental model of what's going on. So I went to Racket and I said, I need a mental model of what's going on in this proof assistant. And it's easy to do prototyping, easy to write quick and dirty little programs in Racket that model something. So I was modeling a little proof assistant. And as I did that, I said, okay, this is kind of interesting. First of all, I now understand proof assistants better and I can answer these students' questions. And second of all, I think this is a solution to the problem of that I was having with proof earlier, and the problem that I was having in the third course I've written down, which is CS245. So CS245 is a course at Waterloo that is called Logic and Computation. It's like, there's a course similar to it in math at Stony Brook. It's Math 371, which is logic, but it doesn't have the computation part in Stony Brook, where in the Stony Brook course, they talk about Gödel's incompleteness theorem and things of that nature. The last few weeks in our course instead talks about proving things about programs. And in a conventional version, it's very conventional propositional and predicate logic, followed by 3 weeks of proving things about programs, which culminate in a proof of a sorting algorithm, which, if you look at the algorithm, it's obvious it works. It's very short, but the proof of the algorithm goes on for pages and pages. And the conclusion that the students walk away with is, this is completely impractical, and this whole course has been pointless. Formal proofs are long, and they're tedious, and they're boring. And that's the whole point of the informal proofs, that stuff is left out. And what you do is you skip over things, and you just have the interesting parts. And that's cool when you are an expert talking to another expert. It's almost like you were Like you're walking with your parents when you're a little kid and they say, oh, don't step on the sidewalk square. We'll jump over it. And you jump over that sidewalk square each time and you learn you're supposed to jump over the sidewalk square, but you don't know why. Is there a bomb underneath? Is there a troll? Is there a big hole? What's going on here? And that's the way a lot of people learn math or are asked to learn math, is when you do something wrong, they say, no, that's not the way we do things. You have to learn indirectly what the things are that are being left out in an informal math proof. But putting those things in is boring and tedious. But boring and tedious stuff is what computers are there to do for us. Also, they're fast, so that's cool. So what we can do then is use these computers to help us do the boring, tedious stuff, but make sure that it's all present and tell us when we're making a mistake, why we're making a mistake. So that's the idea of a proof assistant. But because we have Racket and we have this silly little program I wrote that acts like a small proof assistant, what I decided to do was the following. To take that logic course, and you'll notice that on the slide it says 245E. The E stands for enriched. So this is like an advanced version of the regular course. And as with Math 250, you have sort of the freedom to experiment a little. So what I decided to do was say, instead of teaching conventional propositional predicate logic and boring the students, let's have them start with my little program, a simple version of it. But then instead of my adding features to the program like I did when I programmed myself, I'll ask them to do it, and they will add features and learn. Because when you have to implement something, you have to get everything right. You have to really learn it. And then they can use that tool that they just created to do their logic homework. And that's what we did, first for propositional logic and then for predicate logic. And then in the last few weeks, I introduced them to a real proof assistant, the one that Pierce used. And that was the course 245E. So I started teaching that, and by this time, Taras had just about graduated. I think he was bored that summer because he came and sat in on my lectures, and he said, oh, this is cool. I'll file this away for future reference. And when he got a chance to try and use all of these things in Math 250, he's using it. So, I mean, it still probably looks a little weird because there's all this computer stuff and all this non-standard stuff going on. But when you think about courses like Math 145 or CS 145 or Math 250 conventionally, what do they want? They really want, Math 250 conventionally is mostly about number systems. It's about the integers and the rationals, quadratic field extensions, imaginary numbers, and so forth. That stuff doesn't really show up a lot in subsequent courses. Like the uniqueness of prime factorization, it just doesn't play a big role in future mathematics. It's not about the content. What the course is really about is how to do mathematics. And what Taras is showing you is something more and something fairly precious. It is how to do mathematics in such a way that you're aware of what you're leaving out. You understand the details. You don't necessarily have to work them out, and you know there are ways that they can be worked out with the help of computers. In what follows in your future courses, you're not going to see the lambda calculus. You're not going to be asked to use Racket. But these tools are in your head and on your computer, and you can go back to them and make use of them as needed. They're going to give you an additional perspective, which is going to be really valuable. It's hard to see when it's all coming at you really fast. But I really do believe watching this, that in a few years, you'll look back and say, wow, that was really something. Anyway, that's enough of context. there is some actual material we have to get to. So let me talk about that. So I took my 245, I had fairly sparse slides. I did a little bit of board work, you know, like Taras is doing in deriving the inference rules interactively. But what I did afterwards was post course notes. And you saw what Taras had posted some of those, but he didn't really have time to do a full job. My course notes were refined over a couple of offerings of 245. And then fairly recently, I made them into sort of a self-contained miniature textbook. More than course notes, but less than a full textbook. And because I live in a socialist paradise, which is Canada, and was generously subsidized to do all this work, I've just put it on my website as a free resource, so anyone can use it. So it's going to be a resource for you when you do this next part of the course. And it's called Logic and Computation Intertwined. So let's take a look at it. I'm sure Taras has sent you a link, but if you lose that link, my name is pretty distinctive, and if you search for my webpage, you'll find it. It's deliberately retro, and if you find the French word flânerie, which means, in French, it means a casual walk or stroll. This is what I've been calling these things I've been posting online. So there's a bunch of things here. There's one called Teach Yourself Racket, which is very brief, and that might be a useful reference for you, or if you're interested in particular details of Racket, or if you want another perspective. Scrolling down, there's this stuff, Functional Introduction to Computer Science, which isn't ready yet. It's going to be the 145, 146 stuff, but I want to point this out to you, the Lost Preludes. This is, it contains the original notes from the original first lecture that Taras saw that inspired his first lecture to you, and a reimagining of it in 2020. I did this just a month ago, using a proof assistant, not the one that Pierce used, but another one called Agda, which I spend a lot of time on in Logic and Computation Intertwined. That's something that you might look at later on when you have time. Just keep it in mind. So LOTC is here, and if you click through, it looks like the documentation for Racket, because I'm using Racket's documentation language called Scribble, which is implemented in Racket. It's a really nice way to generate web pages and to generate documents. So my slides, for example, are done using Scribble in Racket. So Logic and Computation has an introduction, which you can skim if you want. The main thing is to look at chapter 2, propositional logic. That's what we're in right now. And you will move into chapter 3, predicate logic, and hopefully get to the point where you can take what you did in that first lecture, which is talking about why 0 is the identity for plus, and actually prove it in the proof assistant that you're implementing. That's Taras's goal, and I hope he has time for it. It's ambitious, but Taras is nothing but, if not ambitious. So there's a little more in LOTC. Chapter 4 talks about the two proof assistants, Agda and Cook. And having worked with Agda more recently, I think it's the better one to start with. I have a whole bunch of new material on using Agda, and there's some little recordings of interaction with Agda, which you might find interesting. But again, this is something you probably want to reserve for afterwards. Chapter 5 has all the files, the various versions of the tool and auxiliary files. Taras may want you to use those, or may supply you with his own versions. I don't know. You'll have to ask him. And finally, chapter 6 is a bunch of links to other things, resources that you're not going to have time for now, and you shouldn't look at now anyway. You should look at afterwards. Now, you may not want to go on in this stuff, but there's, whether or not you do, there's at least one reference in that resources chapter that I think is quite valuable for you. And that is the Stanford Encyclopedia of Philosophy, which is a free online resource. And it's a good way to learn a lot about the history and philosophy of mathematics. Okay, so that's Lassi, and it's available to you. I'm just going to talk for briefly here. I was originally supposed to talk for 30 to 45 minutes, but like Taras, I tend to say too much. So
Don't worry about the end time.
we'll try to keep this short, but I'm around. So if, of course, Taras is your instructor, but if there are particular things about Lassi or if you want a second perspective or a second opinion, feel free to email me at any point during this course, after this course, 5 years from now. I'll be happy to talk to you. Okay, let's get back to the slides. All right, review. This was supposed to start today's class. We're a little bit behind in the timing here. So we're talking about propositional logic, which is a simplification that focuses on the logical connectives, implication and or not, or negation. Later on, we're going to, or you're going to add in the quantifiers for all and there exists. And variables will go away and be replaced by the things that are being quantified over. There exists X. And then you're going to say there exists X, which is a natural number or something like that. So you need things that are quantified over. And then you need ways of taking, making statements about those things. So you need equation, equality, you'll need inequality, you'll need relations that say something about, that talk about objects and let you form logical statements that can then be hit with quantifiers and connectives. So that's where kind of you're heading. But so far, all we have is one connective, which is implication. And Taras has stressed the Brewer-Hating-Kolmogorov interpretation. There's going to be interpretations for all these connectives. Do not panic at this point. I don't know how to speak Russian. So I thought in the transcript, what the transcript did with Taras's Russian was really hilarious. Okay, so the BHK interpretation is a way of saying for each connective, what would a proof of something that has that connective at the top, like a logical formula where that's the top of the abstract syntax tree, what would that look like purely in terms of proof without dragging truth into it? And the BHK work was done turn of the century, 1920s, that sort of time period, before there was computation, before Church did his lambda calculus stuff in 1940. So it's older, and originally it didn't use the word function. It just said a procedure or a method. But now that we have functions, that is a natural way to talk about things. And I guess something I forgot to say when I was talking about the first slide is that the conventional way of doing all this stuff goes through propositional logic, goes through predicate logic. And I discussed this a bit in Lassi. It's deeply unsatisfying because it doesn't seem like you're doing anything of substance. And then okay, I have lost my train of thought, so maybe that will come back to me. Sorry about that. I'm rusty. Okay, let's keep going. So the BHK interpretation for implication is a proof of T implies W is a function that consumes a proof of T and produces a proof of W. And this actually, and Taras has done this, this actually corresponds to what we do intuitively when we assume T and use that to prove W. What we get is not a proof of W because there are these assumptions in T. But if you substitute the proof of T for the assumption, you get a self-contained proof of W. So it really does take a proof of T given later and convert it into a proof of W. And now I remember the point I was trying to make is that in a conventional coverage of predicate logic, you have to go to a lot of work to introduce computation. If in the unconventional way of dealing with predicate logic that we're about to see, the work you have to do in order to do the implementation is work you really should be doing anyway in a conventional presentation, having to do with what is substitution and things of that nature. And it's work that is sometimes glossed over and sometimes sort of, well, you understand what we mean by substitution. You've done it before. It turns out to be tricky to define if you don't want to make mistakes. But then you have to go through a whole bunch of more work to define a model of computation and talk about it. And this is the nice reason to use Racket in a course like this, is that Racket has this nice, simple computational model, and it happens to be exactly the one you need in order to think about propositions as types and proofs as programs or functions. And furthermore, once you do that work in predicate logic of getting all the details right, you've implemented substitution, so you get computation for free. You don't have to do any more work. It's beautiful. And it really pays off in the end. So I hope you get that far with the time, and I better keep going, otherwise you won't. So to review, we have a human readable notation for types, capital T, and terms, little t. Taras has already been using a bunch of different words for these concepts, right? So a type is also a logical formula or a logical statement. And a term is also an expression in a programming language, and it's also a proof term. It's a proof. So you should get used to this because Lassi does it too. And having these multiple perspectives, you can switch back and forth, and it really is valuable. You have to take my word for it at this point, but as someone who's done mathematics for his whole life and continues to do mathematics, it's really nice to be able to think of proof as this active, as in this active way of actually being a function that does something. So far, we only have implications. So that's at the top. We see that a type is either a propositional variable X or it's type, arrow, other type. And here we're fortunate that there's a visual pun in that the right arrow means not only in logic, it means implication. It has for a long time. But also in math, it means the function space, right? A function from the natural numbers to the natural numbers is n arrow n. That's standard in mathematics. So here, those two things really are the same thing as far as we're concerned. It's a nice visual pun. The bottom of the slide, we have the notation for the lambda calculus, Church's lambda calculus from 1940. And Church was a logician. He was working on logic at the time. The logic turned out to be inconsistent. He had to get rid of the logic part, but what was left was the computation part. And then later on, people figured out that there was this correspondence between logic and the typed lambda calculus. So in lambda calculus, what we have so far is a term is either a variable, just a reference to a variable, or it's a lambda x dot t, and this is Church's original notation. It shows up all over the place. It's nice to know about it. Function application, which is just juxtaposition, right? Putting one thing next to another thing is multiplication in a lot of math, but it's convenient to have it be function application because you do so much of it in the lambda calculus. And there's a fourth thing on this slide that I've added that we're going to need, which is the ability to annotate a term, little t, with a type, capital T. So little t colon has type, capital T, and that'll come in useful later.
We haven't seen this yet, so this is new.
That's right, this is new. You should have seen it, but we're a little behind schedule. Okay. So this is fully parenthesized, which you need to do to make things unambiguous when you're reading them, but there are human conventions to take off parentheses. So for example, you can take off the outermost parentheses in a complex expression. They're not needed for grouping. And for arrow, we say it's right associative. So that will let us take off certain parentheses. So instead of saying A arrow parenthesis B arrow A, we can just say A arrow B arrow A. And the grouping is understood because it's right associative. Similarly, in the lambda calculus, we can take off the outermost parentheses. Function application is left associative. So if we say A applied to B applied to C, that's like A applied to B in parentheses, result applied to C. And you already saw that with S's and Z's. That's why we had to put parentheses the way we did around S applied to parentheses, S, Z. Otherwise, we'd have the other interpretation. And finally, lambdas extend as far as possible to the right. Lambdas are right associative. That one takes a little more getting used to.
I have a question
Yes, Amanda.
from the previous slide.
Okay.
What information do you gain by parentheses lowercase t, lowercase t? It just feels a little redundant.
This right here?
Yeah.
Okay, so this is grammar, remember. So little t stands in for any term. And when we have two occurrences of little t in a grammar, they're understood to refer to completely separate things. They're not the same thing. In an inference rule, they are the same thing. But in a grammar, they're different. So all this rule is saying is in order to express function application, we take some term representing the function being applied. And that could be something that's complicated. You might have to reduce that to a value, to a lambda, before you can do the application. And some term representing the argument, so Taras used the meta variable A to refer to argument in what he was doing. And that could be a complicated term. But you take the complicated term representing the function, the complicated term representing the argument, and you put them next to each other, and that means the function applied to the argument. Does that make sense?
So even though they're the same letter, they might not have the same value?
Exactly. And that's the way grammars work. These grammars are called context-free, meaning when you see a variable in the grammar, it doesn't know anything about what's outside. You treat it as a brand new thing, and then you can rewrite it using the rules of the grammar.
Oh, I see.
Right?
Yep, that makes sense. Thank you.
Okay. Any other questions?
So why are functions and arguments like classified as like the same thing, like they're both t's?
The T here stands for term, right? And this is just saying the body of a lambda, which is the body of the function, right? So in Racket, you have this too. You have the function header, which says define name of function, name of parameters. And then you have an expression, which is the body expression. That is formed by the same rules that we're looking at. So that can be anything that is formed by a T. So lambda x dot x is a T. It's a term. But also lambda x dot lambda y dot x applied to y is a more complicated term that I've gotten just by applying these rules to describe it. I'm sorry, I don't have a pad here to be able to draw, so you're going to have to visualize some of these things. Did I help there, or do you want to?
Yeah, I think I get a little bit better.
All right. Anyone else? Okay. So there are going to be three different kinds of lambda expressions here. There's going to be the ones you know from Racket. That's the first time you saw lambda, where lambda was spelled out, but there was also a special keystroke where you could actually put a lambda in. So that's in Racket. And then there's these human readable Church's lambda calculus notation, which we use on paper and for brevity. And then in the proof assistant we're going to be developing, there's going to be a third version of lambda, which has some of the parentheses there, and the dot has to be replaced by something else for reasons I'll explain. So hopefully you can keep all these distinct because they come up in very different contexts. But the human readable notation is nice because you can put it in line and it's easy and you know what you're talking about. Okay, let's keep going. So Taras just started to explain these two ideas of checking and synthesis. And these arise quite naturally once you have the basic idea of the proof tree and the basic idea of representing a proof term by a lambda calculus term. And remember that lambda calculus term encodes the proof tree in the sense that we can mechanically get the proof tree back. So type checking is, in effect, without drawing that whole tree out, just verifying that it exists. So the sequent here is a relation between three quantities, gamma, little t, and big T. And it says these three quantities have the following relationship. Right? Equality is just a relation between two things. What's on the left side of the equal sign and what's on the right side. Here we have a relationship between three things, but it's a similar idea. What is the relationship? It says, well, given the assumptions in gamma, we can prove that capital T holds. We have a proof of it. And that is encoded by the term little t. And the checking process is verifying that this whole tree, the proof tree that is supposed to be encoded in little t, actually exists. Now we can say that about any three things, and it might not be valid, it might not be accurate. So we have to verify that this actually holds. And type checking, as we'll implement it, will either say true, or it will signal an error, hopefully with some useful information. But as part of type checking, and Taras pointed this out, it comes up when you're checking an application. An application alone doesn't have enough information to be able to just use checking. That function, the type of that function has something hidden in it that has to be synthesized. So that's the reason for type synthesis. And type synthesis has the arrow going in the other direction, where you produce the type T rather than being given the type T. And so in type synthesis, you're only given the context and the proof term. And you can synthesize the fact that from those two things, there exists a complete proof tree that proves that little t is a proof for big T. This is called bidirectional type checking because you're going in two directions. And the notation here with the arrows is pretty standard. Although sometimes the arrows go up and down, which I find really confusing. And sometimes people use plus and minus, which is even more confusing. I just mentioned that in case you see it elsewhere.
Question?
Yes.
When you introduce the word type here,
Yes.
do you mean like data type or something else?
So we have, again, this is one of those things you have to get used to. We have two ways of looking at things like this. One is that it's a logical statement, and that this thing is some encoding of the proof tree. The other is that this thing is an expression in the lambda calculus And this thing is the type of that expression. So you can think of this thing, let's not think about the lambda calculus, let's think about a racket program. You can think of this thing as a racket expression, like plus. Plus has a type which is nat, arrow, nat. It consumes a nat and it produces, no, nat, arrow, nat, arrow, nat. It consumes two nats and it produces a nat, right? Let's do square. Square is simpler. Square consumes one nat, like 4, and produces a square, like 16. So square has type nat, arrow, nat. So that's a way of thinking about square, and its type nat, arrow, nat. But in the lambda calculus, you can, the types are things that you can interpret as logical formulas. And so there are these two views we keep flipping back and forth between. Types are equivalent to logical statements, and terms, or lambda calculus terms, or proof terms, are equivalent to programs or expressions in a functional programming language.
In the present realm of discussion, both were also defined by the grammar on the previous page.
Question.
Yes.
So for like the like, you know, racket program thing that you said, in that case, like for like square, what would the gamma be?
So in a racket program, you can possibly think of gamma as all the predefined names. So plus, if you go to beginning student and you use plus, the plus sign, that's a function, right? You don't have to define it, it's predefined. But it's bound to some value, which is the code that actually carries out the operation. So all the things that are predefined form the context. Now, if you use y in your program, and it's not predefined in Racket, and you haven't put a definition in your Racket program anywhere, Racket will complain, I don't understand this. It's not in the context. So that's what the context is in Racket.
Wait, so in some sense, the process of checking like that all your variables are defined is like type checking?
The process of checking that all your variables are defined is something that has to do with contexts. Now, types are not explicit in Racket, and Racket is not a typed language. Okay, it's not statically typed, it is dynamically typed. Types show up at runtime. If you try to add two strings in Racket, you will get a runtime error. You will not get an error. It's not a syntax error. It's not a compiler error. You can put that into your program and it will not object until you run it. But some other programming languages are statically typed. So Java is statically typed. C++ is statically typed. In these languages, every expression has a type, and the compiler has to be able to figure out that type, or it will complain and not let you run your program. And in that context, the computer verifying that your program can be compiled involves type checking. And it's type checking that's similar to what we're doing here. Does that help?
Yep.
All right. Anything else? Other questions? Okay, so let's look at what the bidirectional rules should be. This is supposed to be a review, but it's not. I presume Taras will give you copies of these slides, but in any case, all of this stuff is in lossy, so you'll be able to find it. So here is a bidirectional rule for checking that a lambda expression has a function type, T arrow W. And it is checking because the arrow is going from the type to the term. So the type is being provided, and we just have to check that this expression has that type. And in order to do that, we peel off the X. We know that the function type consumes a T and produces a W. So X, the variable in the lambda, must have type T. We put that into our context because when we're working with just T, it's going to have occurrences of X in it. And we need to remember, for typing purposes, that X has type T. Let me say that again from the proof perspective. From the proof perspective, we're trying to verify that something can generate a proof of T implies W. We pull off the T and add it to the context as an assumption. That assumption has proof X. X is going to show up in T, and when it does, it's using that assumption of T. It's a point where we say, I need to use the assumption T. I'm going to put an X here, and that's what that's going to be. Those are two perspectives on exactly the same thing. And they're used to justify this rule, which is implication introduction, but for type checking. Now, we saw that type synthesis was necessary for function application. So let's take a look at that rule. In order to synthesize the fact that an application of F to A, where F and A could be complicated expressions, in order to synthesize the fact that that has type W, we need to synthesize the type of F. Oops. F had better be some function type, so it had better have the form T arrow W for some T. Why? Because when we apply it, it's got to produce a W. So that forces this. We don't know what the type of A is. There's not enough information here. So synthesis will get us the value of this T, and then we can use that in checking that A has type T. And that is implication elimination expressed as synthesis.
Question.
Yes.
Why in the context for the line above, why is the F is such that type F goes from T to W? Why is that to the right of the turnstile? That's a part of the context, right? No? So shouldn't that be like to the left of the turnstile with the gamma?
No, in this rule, we have not added any assumptions. Assumptions get added only for implication introduction. Or in typing terms, variables get added to the context because we have to remember what type they are, and variables only show up in creating a lambda expression. Here we are applying a pre-existing thing, F, which is, it could be a very complicated expression, but it's supposed to represent a function. If we evaluated F, it would represent a function. We're not actually going to run any of these programs. We're just doing type checking. And this is the weird thing, that proof checking is type checking. And when we get to the proof assistant, it's not going to, even though it's talking about computation, it doesn't do computation in the sense we're used to, in the sense that Racket does. It just looks at programs and thinks about them. Okay, but Why is F to the right of the turnstile? Because what we're trying to do is take this sequent and say, what are the premises, what are the things we need that will let us conclude that F applied to A has type W? One of the things we need is that F produces a W and is a function. F produces a W and is a function, but that function has to have some type T, and A has to have that type. But we haven't added to the context because there's no new assumptions. So the context below is the same as the context above.
But isn't that an assumption when you say that, aren't you assuming that F is a function and that F goes from T to W?
No, this is, okay, so this is an inference rule. Down below is the premise, is the conclusion, right? It's what we're trying to conclude. Up above are everything we need in order to make that conclusion. Those are the premises. The premises are what we need to make the conclusion. Once we've established that those premises are needed, then we proceed to treat them as conclusions and put rules on top of those. And then we build up a proof tree. And when we are completely out of things to do, when there are no more premises left, we have a complete proof tree. But right now, this is just one rule in the middle of the proof tree that says, here's a conclusion we want. Here are the things we're going to need. What are those things we're going to need? They're not assumptions. They are steps towards a complete proof tree.
Okay, I guess my confusion is with what the turnstile represents.
The
What is it
turnstile,
exactly?
the turnstile is just a marker. What does the equal sign represent? It's saying that I'm putting two things in juxtaposition and I want them to have this particular relationship. The turnstile is separating the context from the term. It's just a marker. Just like the dot in the lambda calculus is separating the variable from the body so you don't get them confused. This is just separating the context from the term, and this is separating the term from the type. And when we put the together, the fact that we're using turnstile and not some other symbol, and the fact that we're using right arrow and not left arrow, means that all of this is a sequence that is talking about type synthesis and not equality or inequality or any other relation.
Okay.
Turnstile takes some getting used to because you haven't seen it before, but it's very standard in logic and it's very old. I mean, very old in computer science terms. It goes back to Frege in the 1890s or something like that. It's not old in math terms. But all this stuff, all this formal logic is relatively new. It's late 19th century, early 20th century. I do a little bit of talking about the history of logic in Lassi. Okay, other questions about implication elimination? Okay, so the third rule is relatively simple. It says we can synthesize the type of a variable, and we can do that if we can look it up in the context. Now, there could be lots of things in the context, and this rule is a little bit of a cheat. Really, you should have a couple of rules. One to say, if it's the last thing in the context, we can do this, and that's what this rule looks like. And we should have a rule that says, if the last thing in a context is y:w, then throw it away and try again with the smaller context, because you need to root through that context looking for x. That's what we'll actually do in the program. So the rule is a little bit of a cheat here. Okay, so now we have one synthesis rule and two synthesis rules and one checking rule. This is not a complete set, right? And because we have two concepts, checking and synthesis, and we have three constructs in the lambda calculus. So we should have 6 rules. Well, what we're going to do is get away with 5 rules. And the remaining rules are going to apply when these rules don't apply. And the remaining rules are going to say how we switch from checking to synthesis or from synthesis to checking. So let's take a look at those last two rules. Questions on this slide before I leave the slide? Of course, we can come back to it if necessary. Okay, so here are the two rules. The easier rule is the turn rule that says, suppose we're doing checking and we don't have a rule on the previous slide. Well, in order to check that term little t has type big T, we can synthesize using just gamma and t and make sure that what we get is big T. So this goes from, well, if we need to do a check and we don't have a rule, let's do a synthesis instead. And this is called the turn rule. It's turning the arrow around. That's what we really do in the code. We check to see if a rule applies for synthesis. And if not, we just recursively call the other function because we're going to do synthesis. What about going from synthesis to checking? Well, synthesis is harder than checking because in checking, you're given the type capital T, and in synthesis, you're not. You have to figure it out. So if there isn't a rule for synthesis, are you always going to be able to check? No, sometimes you can't. Sometimes you don't have enough information. So we have to put some additional information in order to go in this direction. And the additional information is this annotation. If we have an annotated term that says the term little t is annotated with the type capital T, that forms a larger term. And if we're asked to synthesize the type of this term, we can do that. That's easy. We just pull out the capital T and check that it's valid for little t. So if we're asked to synthesize an annotated term, then we just check. And the code does that. Now, this still doesn't cover all situations, but the situations that it doesn't cover, we have to raise an error because we cannot carry out the task.
A question, what does turn stand for again? I know the N is for annotated.
Turn? Turn here, I just needed some word. And it's turning this arrow around. So it doesn't stand for turn style, it stands for just turning. Okay. So now I want to introduce the tool, the silly little program I wrote. And what you're going to see is I'm going to give you a high-level description of it, and then Taras is going to go through the actual code and teach you some of the additional features of Racket that you need. I'll talk a little bit about those. The tool is called Proust, and all it is a small Racket program that does both type checking and type synthesis. So there's two main functions there. Proust, the word comes from the name of the author, French author Marcel Proust. Now, Marcel Proust was writing at the end of the 19th century, early 20th century, and he wrote a series of 7 novels, which in French, the title of the whole series is Recherche de temps perdu. In English, it's often translated in the English books, the translation is remembrance of things past. But literally what it translates as is in search of lost time. And that is the translation you'll find on some, there's a recent retranslation of the novels. The novels are famous, they're very long, and they start off with a scene where the protagonist has a madeleine, which is a little French biscuit cake, very nice, lemony and buttery, and the protagonist dips it in a cup of herbal tea and takes a bite. And this evokes a memory in the protagonist's mind, which expands into this series of 7 novels. It's considered one of the sort of great things to read if you're obsessive about reading. What does this have to do with logic? Absolutely nothing. The only reason I chose Proust was that if you say proof assistant really quickly, and we have a small proof assistant, so we don't have a lot of time to say it, it sounds like Proust. That's the only reason for it. So Proust is a series of programs starting with a simple one and then adding a little bit of code each time to add more features. Some of the features you'll be given, and some of them you will implement yourself. So I want to go over the high-level architecture of Proust. It's a grandiose word because the code I'm talking about is less than 100 lines of code. That is nothing. You know, in Java, you can barely do hello world in less than 100 lines. It's but Proust proof terms are just going to be S expressions, and they're going to need more parentheses. So we're going to put the parentheses back. And we can't use dot like we do in the lambda calculus because dot has a special meaning in Racket. So some changes here. Hopefully they're not too confusing. Type is fully annotated, and the arrow is formed by minus and a greater than sign. You can do this with Unicode, but I thought it'd be a little easier here to not do a lot of Unicode. Similarly, expressions, instead of the dot in lambda calculus, we have this double right arrow. Hopefully that's not going to be too confusing with respect to type synthesis, because it's the same double right arrow, but it's, in this case, it's formed from an equal sign and a greater than sign. And this lambda, it's easy to do in Racket, so I thought that was okay. And then function application is just like in Racket. Annotation, well, you have to put a space, you have to put spaces in. So this is really a list containing 3 things. It's containing a nested list, which is the first expression, the symbol, quote, colon, and a nested list, which is describing the type. But that's just a little bit of change of notation and a few more parentheses so that we can write things as S expressions. So we're going to be working in full Racket, hashlang Racket. So we leave the teaching languages and go into full Racket. There's a lot of stuff you can do in the teaching languages. I mean, there's a lot of stuff you can do in full Racket that you can't do in the teaching languages, and we're going to make use of some of that. The price we pay is that some of the safeguards are gone. For example, if you try to const 1 onto 2 in the teaching languages, you'll get an error. It will say 2 is not a list. You can only const a value onto a list. If you try to const 1 onto 2 in Racket, you can do it. You will get something that displays as open paren 1 dot 2. That's the special meaning of dot. You don't want to do this. This is not something you want to do, and I'm mentioning it because if you make a mistake and const something onto a non-list, you will see a dot show up. And that's a sign that you've done something wrong and you need to fix it. So the safeguards are gone. But other than that, things are pretty similar. Instead of hash true, the value that is displayed is hash t, but you'll get used to that really quickly. There are a few things that are really useful. Pattern matching is something you saw on the first day because Taras used it in defining plus, right? He said plus x and then s applied to y, and s applied to y on the left-hand side of the equal was a pattern. And he talked about that. Pattern matching is useful because without pattern matching, you might have to construct a very big, messy if expression or conditional expression, and it's not very readable. So you can do without pattern matching, but pattern matching makes programs more expressive. And the point of using it in Proust is to make the code really readable and as close to the inference rules, as close to the paper definition as we can get. For the same reason, quasi-quoting is useful. This is an extension to quote, which lets you escape and stick in things. And you can do that in list expressions. So you can have a list 1, 2, 3, but you can replace 2 by a computation and you escape in a special way. Tars will explain how that's done. And that makes code a little more readable than using const or the racket list function. You can also do that in patterns. You can describe a pattern by saying, okay, I want a pattern, I want a list where the first thing is a string, and let me call that S, and the second thing is a number, and let me call that N. And then you've done a bunch of stuff that you can do with a conditional expression, but it just looks very readable, and it makes Proust a little easier to understand. And it's important to understand Proust because you're going to be modifying it, but you're going to be modifying it in little ways that are within your capability, even with what you know of Racket. You don't have to do complicated programming. You just have to kind of extend the kinds of things that are already being done for you. So here's the high-level description of what you'll see in Proust. What we do is we take these S expressions, which are just taking this grammar and building, for example, an annotated expression, which has a sub-expression, a colon, and type, and putting a quote in front of all of that to make it into an S expression, and then feeding it to Proust. And what Proust does is it takes this thing, which is a nested list, and it makes it into an abstract syntax tree. And that's called parsing in general. In general, it's quite hard, but with S expressions, it's really obvious. Right? If you try to parse arithmetic expressions of the kind you see in your math textbooks, that's tricky because there are a lot of hidden rules there, like multiplication is done before addition. We don't have any of that here. We have S expressions, so you'll see that parsing is just straightforward structural recursion on the S expression. And we define some structures to have different types of nodes in our abstract syntax tree. And this is just to make the code that deals with the abstract syntax tree much easier to understand. We could have just had that code work right on the S expressions, but then the code is harder to read. So there are two routines that do that. Parse expression consumes an S expression and produces an abstract syntax tree for the expression. And then parse type does the same thing and produces an abstract syntax tree for the type. Later on, we'll have to put these two things together, but right now they're separate. Okay, continuing with the architecture. We want to go the other way and take an abstract syntax tree. You can print that in Racket. Racket will print everything except functions. It won't print a lambda. But it's not necessarily very readable. So pretty printing is taking a data structure in general and producing a visual representation that a human can read. So in this case, pretty printing an expression will consume an expression and produce a string, which then we can do various things with, such as display it in the interactions window. And then pretty printing for type does the same thing for type. And again, these are just descending the abstract syntax tree, creating pieces of strings and then gluing those strings together. There's nothing remarkable about this code at all. The heart of Proust is type checking and type synthesis, and they're two mutually recursive functions. Just like the definitions are 5 rules for type checking and synthesis in a bidirectional fashion, we're mutually recursive. And these two routines, type check and type synth, all they do is literally implement those 5 rules. There's nothing else there. So for checking, we need to consume three things: a context, an expression, and a type, and produce a Boolean. That's an overstatement because we either produce true or we error. We never produce false. And then similarly, type synthesis consumes a context and an expression and produces a type if it doesn't stop with an error because it can't do its work. So the errors are always a possibility here. So I said I wasn't going to show you any code, but here's a little bit of code just to give you a flavor of how we do things. So in full racket, check expect is not predefined. That's built into the teaching languages, but there's a library which has check expect in it. And so here's the magic invocation, which calls up the test engine library and subdirectory racket tests, which gives us check expect. Now here's a use of check expect down at the bottom of the slide. And I want you to focus on this S expression in green. It's an annotated term. On the left is an expression, and it's lambda x dot lambda y dot x expressed in Proust syntax. And on the right is its term, its type. A implies B implies A. And what we want to do is check that this is a proof of A implies B implies A. How do we do that? Well, we have an annotated term, and the thing we can do with an annotated term is we can synthesize its type. So check proof in general consumes P, which is a S expression, but it's an annotated S expression. So it's a proof with a annotation of what it's supposed to be proving. I've got my hands mixed up, sorry. It's a proof with an annotation of what it's supposed to be proving. And we parse that into an expression tree. And it's going to be an expression tree for the annotated expression. And then we feed that to type synthesizing with an empty context. Now remember that racket, this is full racket. And I remember either in the lecture or in Piazza, one of you said, how do I do more than one thing? And in a conventional programming language like Python or Java, you do multiple things and get things done through side effects. You can't do more than one thing in the teaching languages, except in the very last one, advanced student. But in full racket, you can do more than one thing. And here's how you do that. You just list off the things you want to do. First, we type synthesize. If this fails, our proof is wrong. If it succeeds, what's it going to do? It's going to give us A implies B implies A. We already knew that. It's useless to us. So we throw that away and we produce the value true. And that is what we check for in the check expect. So if our test succeeds, then the check expect will say, yeah, test succeeds. If our test fails, it's going to be because type synthesis failed, and it's going to be because this term does not have this type. Okay, so that's how we would use this version of Proust that I sketched for you. And this is provided for you in basic Proust for implication. But it's a proof checker. There's no assistance. You have to provide it with that complete proof. Otherwise, it's not going to create it for you. So how do we do proof assistant? Well, a proof assistant involves interaction. And interaction means some user interface, and user interfaces are complicated. They're hard to code. They're hard to understand. They're hard to design. We want a quick, dirty, simple, silly program. We don't want to do all that stuff. But we have Racket, and we have Dr. Racket. And Dr. Racket has the interactions window, the read, evaluate, print loop. So that's what we're going to use to interact with the proof checker to turn it into a proof assistant. And because we interact in the interactions window by typing something and then seeing what it does and then typing something else, you know, our mood changes depending on what we see. And similarly, to communicate between those two computations, we can't do it. There's no way to do it. In beginning student, you can only communicate from one function to another by passing an argument down. The way we do that communication is by the other thing people tried to do, which is to say, can I have a variable and then change its value? Which is the way you get things done in Java and Python. That in Racket has the word, it's called mutation. You're mutating or changing the value of a variable. It sounds evil, and it kind of is. Racket has mutation, but it's not dominant. It's not used very much. It's used judiciously with restraint, with care, because it's much harder to reason about. The kinds of things we were doing before would not work if there was mutation. It gets messy, which is why that proof at the end of my conventional 245 course about the sorting algorithm, it's why it was so messy. It's because mutation is hard to reason about. If you read on in Lossy, you'll see a section in chapter 4 which talks about proof for a sorting program, and it's much cleaner and easier in a purely functional environment. But mutation is useful in this context, and I'll tell you what we're going to, how we're going to use it. You don't have to do any of this. All of this is set up for you, and you don't have to change it. I'm just explaining it to you so that when you look at the code, this is not scary stuff. It's doing stuff that's kind of straightforward. So if we're going to have proofs assist with proofs, we have to introduce the notion of a partial or incomplete proof. And we do that with one addition to the grammar, a question mark. So now an expression can be any of those things before: lambda, function application, variable, annotation, or just question mark. Question mark represents a part of the proof we have not completed. And again, there are multiple names for it. It's either a whole or it's a goal. It represents something we're trying to aspire to, something we want to finish. So a goal or question mark represents an unfinished part of the proof. And in general, you can have several question marks. What are the type checking and type synthesis rules for a goal? Well, it's pretty straightforward. When we're type checking and we hit a goal, and checking, remember, is provided with a type. So when the type checking function says, does this question have this type? It'll say, sure, whatever you say. I don't know, it's incomplete. You're going to have to fill it in with something which has that type, but for now, fine, buddy, it has that type. So a goal always type checks with whatever type is provided. But there's no way you can synthesize a goal because it's a question mark. We don't know. We have no information about what is there. So a goal always type checks, cannot be synthesized. So that part of it is easy. But now we have a bunch of question marks in our expression. So how do we handle those? What Proust is going to do is it's going to go through and number them all internally, and also provide a way that the user, the person doing the proof, the human being, can refer to a particular question mark. This is question mark number 6. This is question mark number 7, and so on. It's going to keep track of all of those and the type that they should be if if they're filled in properly. So a variable whose value can be changed is sometimes called a state variable. That's just a way of referring to a variable. It's going to be a global variable defined at the top level. And they're going to be state variables for the current expression, because what we're going to do is take an incomplete expression and gradually fill in pieces. And so there's going to be a notion of what are we working on currently from one interaction to the next. There's going to be a table that says for each goal number, what type has to be filled in for that goal. And finally, there's going to be a counter, because if you fill in a goal with an incomplete expression that has more question marks in it, we get some new goals, and they have to have numbers. So we just have to have a counter that says, what's the next number to assign to a goal? And these things are handled in more or less a straightforward way. For the table, we use a Racket built-in version of tables called hash tables. But that's really, you don't have to know how they work, you just have to use them. You can put something into a hash table, you can look things up, you can remove things from a hash table. That's all we use it for. And there's some additional code written, and it's described in Lossy, and you can see it in Proust imp with holes, but you don't have to touch it after this. Code to set things up at the beginning, and code to refine a goal. And refining a goal, I'll show you a demonstration of this shortly, but refining a goal, you give a goal number, like I want to refine goal number 7, and here's what I want to replace that question mark with. Another term which could be complete or could have question marks in it. And some work has to be done there to make sure that what you're doing is actually legitimate. You could think about what that might be. It's not too hard to figure out, but all that's done for you. And if you look at the code for the refined function in the program, you'll see more or less what you expect to see. All of this is going to be in Proust imp with holes, which is provided to you. So the last thing that Taras wanted me to do was to give you a demonstration of that. Is that still on, Taras?
Yes, of course. No, this is perhaps the most important part, because I will assign, well, your PG1 for homework. So
okay.
This is exactly what you'll be doing on the weekends.
All right, so let's get to the demo. And this is, what file is this? This is, it says here, it's Proust imp with holes.
And that's exactly what you'll be using.
And there's just a warning at the beginning that because of the Unicode characters, some browsers don't deal well with them. So don't pull a file up in your browser and then cut and paste. It will not work. It will not work properly. Use command click or right click or option click, whatever it is, to pull up the menu that says download this link rather than show it in the browser. So there's all this code that I'm not going to go through. That's not so important. Taras is going to go through it at some point. And down at the bottom, there are 2 examples that are commented out. So I'm going to do the example that we already saw of A implies B implies A, whose proof term is lambda x dot lambda y dot x. And I'm going to do that in an interactive way. Now you see all the steps of the interaction right here. And so I'm just going to cut them and paste them to show you what happens. So we're going to work in the interactions window. And the first thing we have to do is set up a task. So we set the initial task to be A implies B implies A. So this is what we want to prove. We want to prove A implies B implies A. And notice that the parentheses are gone. So this version of Proust will allow, it knows about the right associative rule. So you can simplify some of the expressions. They don't have to be total parenthesis heavy. When I do that, it responds with, the task is now question mark 0, so that it's provided a question mark. And the entire incomplete proof is a single question mark. It's question mark 0. And question mark 0 has type A implies B implies A. So that's what's happening right here. Now I want to start refining. And the only thing I can do is fill in hole 0. But I can fill that in completely, or I can fill that in partly. Now let's pretend I don't know the answer. But I look at hole 0 and I say, okay, it has a function type. It's an arrow type. So the way I create an arrow type is with a lambda, but I don't know what the lambda body should be. So what I'm going to do is say, I want to fill in hole 0 with a lambda whose body is a question mark. It's a hole. And that's what this statement here does. It says, use the refine function, which is provided by Proust, on hole 0, where you're filling it in with lambda x arrow question mark. So I've said that x is going to be the variable. It doesn't matter what you use. You can use whatever name you want. But the body, I don't know. I don't know yet. I don't know. So let's take that and paste it in. In actual fact, you would type it in. You don't want to see me type. So, and it says the task with one goal is now lambda x arrow hole 1. That whole thing has to have type A arrow B arrow A. But hole 1 is the body of the lambda, so it has type B arrow A. And the context, which is what is the type of the variable x? The type of the variable x is A. So you see the 3 things that you need. The full thing you're working towards, the goal and its type, and in its context. So now, in general, you could have multiple goals, each with their own type, and you have some context of assumptions you're working within. And there are ways to display these things. Let's keep going. Looking at this, the body has to be of type, it's an arrow type. So the body has to be a lambda. So I'm going to refine hole 1, the body of the lambda x, with another lambda, which is going to be a lambda y. So I copy that, paste it. And now the task is A implies B implies A. And what we have so far is lambda x dot lambda y dot hole 2. Hole 2 is type A. And the context has y has type B and x is type A. So I'm done, right? I just have to fill in the thing which
Pose this
is
as a
type A.
question.
What?
Pose this as a question. So let someone figure it out.
But the answer's up there on the screen. Okay, so Taras wants me to ask the question, what do I do now? What do I do? And don't peek above at the program. Just from what you see down here in purple, how do I finish this off? Or can I? Do I have to refine further? So if I refine, I have to refine hole 2. There are no other holes. What can I put there?
X, right?
X.
Or A.
Well, you have to put something that has type A. And
Yeah,
the context says X is type A. So I have to put the symbol X in. Okay, so let's try putting Y in and see what it does. That's not going to work, right? Cannot type check Y as A in context YBXA. It fails. But if I put X in, and the task has no more goals left, I'm done. I have completed my, my synthesis. Now this seems kind of silly because we could figure out this answer ourselves. But there are actually problems for which this actually helps, believe it or not, especially when you start throwing in more connectives. This will actually be useful. And it's surprising. And then when you go to a real proof assistant, which does this in a slicker way, but it's basically doing this, then all of a sudden you've got this helper that's really doing a lot of work for you and telling you when you're making a mistake, tells you when you screw up. And that's really amazing. So, okay, to conclude things and turn back to Taras then, I'll take questions at the end, but just let me summarize that. What you're getting here is all four of those things on the first slide: informal versus formal math, and informal versus formal computation, and they're all intertwined. They all bear on each other, and they represent a space we can move around in. And what you're getting from Math 250 as a whole, this invocation of it, is the ability to move around in that space and know where you are and know how to get to different points in that space. And that is a terrific thing. Okay, I'm done. I'll take questions and turn the mic back to Taras.
So I see how this does type checking for this kind of logical statement. How do you go from here to making, statements and proofs about, the real numbers?
Okay, how would we get from here to something like 0 is the identity for plus? We need to add, for all n, right? We need to add quantifiers. And that takes a fair amount of work. That's chapter 3, and Taras is going to spend a fair amount of time doing this. But it's work that has to be done, and when it's done, we have a program that handles it. And then we have to add the ability to talk about natural numbers. That's not too bad because that's just adding S and Z. You already know how to do that, basically. You saw how to do that in Racket. It's really the same idea. You just build some structures. But what do you need? You need the induction principle for natural numbers. And that gets built in. But once you have the induction, that's all you need. With the induction principle in higher order logic, you have all the properties of the natural numbers that can then be proved. That can be proved in a conventional way. I talk incidentally in Lossy about what a conventional logic course would look like and why I'm not doing it that way. And I try to refer back to, for example, something like your Mat 371 as much as possible, because I don't want this to be some sort of weird thing that no one else talks about so you could never use it. What it is a way of going back and forth between normal land and beautiful land, and you get to choose when to move into beautiful land and do things nicely and then take them back to normal land. It's kind of nice. So we have to add a whole bunch of stuff before we can talk about real things. And what I do in Lossy is, instead of going on with Proust, because I mean, Proust, we're stuck with the interactions window. Now, obviously, Racket, Dr. Racket itself is implemented in Racket. So obviously there's stuff to do, user interfaces, and we could do something slicker, but that would be a lot more code and a lot more work. Other people have already done that work for the proof assistants, Kok and Agda. We just switch over to one of those, and now it's easy because we know what they're doing. And with those, we can make great progress. So chapter 4 is all about how do we prove things about the natural numbers that are interesting. And I go as far as talking about the greatest common divisor and things like that. And how do we prove things about lists? How do we prove things about data structures? So I handle some interesting data structures. How do we prove things about sorting? All of that is in chapter 4 with a little more smarts than what Proust provides at the end of your work with Proust. You can do these things, and it's really quite amazing. There are some serious mathematicians who think that this is the way to go forward. Vladimir Voevodsky, who won the Fields Medal, was heavily into using Kok in order to work with, you may have heard of this homotopy type theory an alternate way of expressing the foundations of math and doing math in this new way that is heavily influenced by and uses these proof assistants. So this is not just a weird computer science thing. There are serious mathematicians who are taking this very seriously. It's a tool that ultimately is in development, but ultimately I think will help mathematicians do their work, which can be very computational. I mean, my colleagues in the applied math department use computers a lot more than I do as a computer scientist. Other questions?
Well,
Okay.
oh, go ahead.
Go ahead. I was going to say, go ahead, Taras.
Yes. Well, if there aren't, let's thank Prabhakar for an excellent talk. I'm not sure if Zoom applause works, but that was really great. Especially, I punted onto you describing bidirectional rules. So sorry for that, but it was a brilliant description. And I'll make a few remarks about the midterm and about this weekend's homework, but let's thank Prabhakar in the meanwhile. So,
Thank you.
This works. Thank you very much. And then I'll take it over from here. So I just have enough time to say one thing about the midterm and one thing about the assignment. For the sake of the assignment, let me just quickly check this, bring this up. Good, it is empty. I needed to check that the solutions to the homework problem weren't actually in the file that I'm about to show you. So this will be your assignment for this weekend. These are the first starting Proust propositions that you're going to be proving. So all of them are in the language of just logic with only implications and propositional variables. So in this case, A implies B implies C, implies A implies B, implies A implies C. And the one thing that I guess I didn't have time to discuss is, and that Prabhakar mentioned very quickly, is the right associativity of implications. So in general, if you have any statement of this form, the way that it's automatically implicitly bracketed is as follows. A, it takes in a single parameter A and it returns a function, A to A. Or A implies that A implies A. So then brackets here are necessary so that the first factor of the implication isn't just an A. The first factor of the implication is this entire term. And then what does that imply? Well, that implies this implication. And so here are 4 problems. Now, there are 2 ways to go about solving this. The first is that you can just stare at the structure of the term, and you can write a lambda term that satisfies this. I was not clear. I didn't have time for the bidirectional rules, and so I would definitely need to spend more time discussing them, but you don't even need to think about the bidirectional rules. You have monodirectional rules, just monodirectional typing rules, which say when rules for typing lambda terms monodirectionally. See if you can write down a proof term that produces, that corresponds to a valid proof tree. So to share back to the document that I had, here, my tablet is connecting perpetually.
So maybe I can say it maybe I can repeat
Yep.
what you said in different words. The purpose of bidirectional type checking isn't to give a way to create proof trees. What it is a way to explain the code which is doing this bidirectional thing, checking and synthesis in two separate functions. You don't have to do that in order to create a proof tree. You can create a proof tree just with the things that were up at the very top of Taurus's blackboard, or with the things that have the lambda calculus terms in the middle, which were not bidirectional. But if you want to understand the proof code, then you need the notion of bidirectionality. That's the only reason it's there.
Right, exactly. It turns out that my tablet is at low battery, so and this application is completely useless for scrolling. But here, we're back at the rules. So you have these rules. These rules allow you to inductively construct proof trees. You look at the conclusion of one of those proof trees. For example, the conclusion here. Or I mean, in the case where there are actually annotated terms. If you have one such conclusion of a proof tree, and there exists a valid proof tree with that conclusion, then let's just give Proust the good faith for the moment, and this will essentially always be true except for one case that I'll outline next week, that Proust will be able to successfully check that that proof tree, that term can be used to reconstruct the proof tree. So you don't have to think about bidirectional rules at the moment for the sake of just doing this weekend's homework. You just need to think about these rules as we've described them and seeing whether you can construct any term which is a valid conclusion, well, the sequence specifically in the empty context, that term has type, whatever the problem specify. I'm not being clear, but going back here. Each one of these problems asks you to produce some term that will witness this type. You can do it just by staring at the term and trying to reconstruct with some bits, or you can do it interactively. And in fact, the way that I encourage you to do it is to do it interactively. Now, you can rewatch the section of Prabhakar's video, of the lecture video where Prabhakar describes how to do this, or you can look at Lackey, where it's described in much greater detail. The notes are really well written, and the process of doing this interaction is described there carefully. Now, so I'll have you download the implication with holes starter code from Prabhakar's websites, and I already sent you a link to Lackey by email with 2 days ago. And also it's on Piazza in the information post. And then you just take this code. One thing that you need to remember is that if you open it and it looks as though your language is set to intermediate student with Lambda, you should switch the language to determine language from source. In general, the language is determined by the first line. Now, you might not see this in your other Racket code, but Dr. Racket actually inserts 3 secret lines at the top, which specify the language in which you're working. If you, for example, download your Marmoset submissions and just open them in text or open them in Marmosets, you'll see that there are 3 lines. So the first line determines the language, and this is why you're setting your language to determine language from source. Now, starting from here, I'll just go with the first problem. You can start an interaction. So once the language is correctly set, that is, determine language from source, you start the interaction, which now has some examples at the bottom. But I now write set task, and I put the term that I'm trying to prove. And now I'm back in this interaction. Now, at the end of Prabhakar's interaction, he got to this proof term right here. So suppose that you go through the same process that Prabhakar went through, and this is your conclusion, which you can print by writing current S expression. In this case, the current S expression will have a hole in it. It'll be precisely what's given here. But that S expression is quoted. On the first programming assignment, I had you put your submissions inside an enclosing set of parentheses and then put a quote in front of it. Quote essentially turns names into symbols. The name, for example, define, well, that's a reserved term in the language. Let's see what it'll say here. Right, it's not a function, it's a piece of syntax. But I can change the define, which has its all of these bound meanings, to just be a meaningless symbol by putting a quote in front of it. And that also happens with lists. If you have a list of values, instead of writing list, the syntax which I've described before, well, full bracket doesn't even write the word list. It writes it in quote notation, which is another acceptable form for lists. And if your lists have names, which may have meanings, or names which are undefined, none of that is scary because a quote will just render the names as meaningless symbols. This is a list. So for example, you can access the second element of the list. Second is a function in Racket. And if you access the second element of this list, it's just the meaningless symbol define. So that's what quote does. And that's why in PG1, I had you quote your solutions. Whatever was in there, even if it didn't follow Racket syntax, by putting it in enclosing parentheses and putting the quote there, it just got converted to symbols, which let me test for whether your solution was right. I just compared for symbolic equality. Now, I'm not going to ask you to put another superfluous set of enclosing parentheses. So let's say we do the demonstration that Prabhakar did. Prabhakar, if I set task again, will it set a new task and completely clear the session, or should I rerun?
I believe it'll completely clear the session.
Right, so if I now go through example 2, this will now run. Well, okay, it'll now produce the output of current S expression.
Yeah.
Right. So you've gone through this process, you finally clear your hole, you ran current S expression, and you get down to this. So when I spoke about S expressions in this course, I always spoke about them as corresponding to ASTs, but where the node label was the first item. There's a more general sense in which these are S expressions. So in this case, this is a annotation, but the annotation isn't the first item. But anyway, it's this quoted list. So you would take that, let's suppose that that's your answer. That's what happens when you run current S expression, and you go in here. Now, if we look what I'm about to paste, it's of the form, here is some term. Annotation, here is some type. Quote in front of it. If you look at each of the input questions that you have, they're defining some name to be this quoted list. And the quoted list has a question mark here. And then it has the type that you're trying to have a term of. You're trying to produce a term of this type. So if this was your output, and this was indeed the question that you had, you'd take what is to the left of this colon inside the enclosing parentheses, and you'd replace the question mark with that. Now, let's, so you do all of these replacements, but you don't just take on faith that these replacements are correct. Define answer 1 is now going to be something like this. So let's say here, that's the question that we want. We can now ask well, we can now ask Bruce to check this proof. How do we do that? We simply say check proof, which is defined at the bottom of this code. Anyway. And now let's say I check proof example 2. So that will be the same thing as had I replaced example 2 with this expression.
I don't think check proof is here. It's in the other file, but it's not here because you have to type synth empty, etc.
I see, that would be a good thing to add. Well, that's not an issue because I have the other file right here. So that's what might be a good thing to add to this file.
Right, I should say to the students that Proust is very bare bones. The error messages are very bare bones. You should feel free to add stuff that will help you. It's a program. You can change it. It's not written in stone. For the purposes of, Taras will ask you to implement certain features, and he will test those features. But if you've got additional code there that does things you want, it's not going to hurt, and you can use it in doing your proofs. It's open-ended. It's up to you what you do.
Right. I'll send you, so this single line about check proof here, I'll send this to you by email. You could also just add this to the other file, as in I'll send it to the students. But if you went to the basic version where now we have check proof defined, and now example 2 is defined in this file. But I just copied the S expression to which it evaluates, this quoted list. And now I can ask Proust to check this, and it'll say true. And when your homework is graded, this is precisely what will happen. So if you take whatever answers you have here, there should be no reason why Marmosets rejects your code. You can be fully certain of their correctness just by running check proof on the answer. So whatever answers you put here, they're going to be some quoted list. Take that quoted list, go into a version of Proust which has check proof, put that answer there. In fact, copy this entire line into this file. And since it's a defined statement, you can write define answer 1. Well, you can write answer 1 in place of this, and you can ask it to check the proof. And if it returns true, then that is the criterion by which your homework will be graded as correct. It's fully deterministic from these input files. Now, in this case, like I said before, there's really 2 ways that you can develop it. One is by going through the interaction. The other is bare bones, which I don't encourage. For example, what is this? A implies B implies A. How, given a proof of A, can I produce a proof of B implies A? Well, if I take a proof of A, how do I produce some function that takes a proof of B and returns a proof of A? Well, what I would return in that function is just the proof of A that I was originally handed. So that proof term should be lambda x, lambda y x. And then we ask, well, what's the Proust notation for that? This is a bit compressed. So here, the delimiter isn't a dot, it's this arrow, lambda x. What, when given a proof of A, do I produce? I produce a construction that takes a proof of B and produces a proof of A. So what do I do? Anyone? Well, I mean, the answer is written above, but anyone? Not looking at the line above. It's really hard to ignore the line that's immediately above it. If anyone's able to ignore it and then give a genuine response. Well, okay, that's a bit disingenuous from the start. So then we start, Okay, now I want some function that consumes a proof of B and returns a proof of A. I'll just call the formal parameter of that function Y. And then what do I return? Well, I need a proof of A. Where is that proof of A? It's X.
Good question. That symbol, is that just a equal sign followed by
A greater
arrow?
than sign.
Okay.
So equals and greater.
Okay. Thank you.
Now, right, so from the interpretations that I had before about proof terms. So this example is a small enough example, like Prabhakar said, where you can reason through it. For more complicated example, the interaction really helps. In fact, that very likely will be the case for some of these problems. I think it is. Yes, definitely. Right, but then look at Lackey or rewatch Prabhakar's demonstration again, and it'll go for an interactive way to produce these proof terms. But once you have a proof term, you can ask a version of proofs that has this check proof line. I'll send it to you by email so that you can add it to this file. Actually, I'll send you the file with this added in. You run it, and it accepts the arguments. So that's how you pass the assignments. And then the only thing that you have to know theoretically going into that is that whatever it is that you're trying to produce, here's a completely unambiguous specification of what the problem is. You would like to produce some conclusion at the bottom of a proof tree constructed from these rules, with the context being empty. Except for the fact that there's a translation between this lambda calculus notation in which there's a dot and the notation in lambda calculus where, because dot is this pair formation, this consing onto potentially non-list values, we replace it with the equal sign and the greater than sign. And then we add spaces between the lambda and the x. And then we enclose everything in another set of parentheses and quote it. But really what you're trying to produce is a conclusion at a proof tree that is constructed from these rules in which this logical formula which you're concluding, or the type of the program that you're producing, is what is specified in the problem. Does that make sense?
It's kind of all new to me.
Right. I'll send an email with a lot more details. And I think my tablet should now be able to connect. I've charged it for a bit. Here we are. Oh, but can you, now's a good chance to ask any questions for clarification. Right. So I'll describe that further in emails, but now I'd like to take a chance to talk about the midterm. So the midterm will start on Monday, a few hours after lecture. It'll run from 8 p.m. New York time on Monday to noon, or to specify what 12 is, 11:59 a.m. on Wednesday. And what will the problems be? Well, roughly, there will be one list recursion problem, possibly asking you to write multiple functions. Well, actually, let's go through it in the order that there were homeworks. There will be one proposition about natural numbers. So proving something about nats, as you did on PF1 and PF2. So the model for this is in the style of PF1 and PF2. Then there will be a racket problem on list recursion. Again, probably having you write multiple functions. And this is in the style of PG2 and 3. Then this week I assigned quite a bit of homework, and very recently, but it's very much in the guise of the previous two problems. A theorem on lists. And this is in the guise of PF3. And a slightly shorter problem on higher order functions in racket. And this is analogous to two programming assignments. The first is PG3, which you can see up on marmosets. And I'm about to add another bonus problem, sorry, PG4. And 5. Now, PG5 is going to be a bonus problem. So it's not strictly required that you do this, in the sense that if you're running out of time, it is not necessary that you do it in order to be caught up on all of the material for the midterm, but it'll help. Then finally, I'll ask you to write some Proust proof terms for implication. This will be a shorter problem. And I'll ask a short written response question. About rackets. And the assignment that I'm about to post on Proust will be known as PG4. Sorry, PF4. So it's very important that you do PF4 this weekend. All of these problems will be submitted under separate headings on marmosets. The release token policy for the programming problems will be very restricted. I'll give you 3 release tokens that can be used during the entire period of the exam. Each of the problems will have a sample input in the problem statements, and that sample problem input will be the public release test. So just to ensure that nothing happens like you name the file incorrectly, you'd only use your release token if you already passed the public test. So I realized that's very much all of the content after the first 2 problems seems to be stuff that has only very recently been thrown at you. This is definitely true for Proust. But as you'll see, when you catch up with this week's homework on proving theorems about lists and higher order functions, it's very much in the same spirit as your first two types of homework assignments. So perhaps the hardest assignments in this course so far was doing the first proof and doing the first programming assignments, and especially the second one with perms. That really hard work should have taught you how to solve such problems. And then to hone your skills further and also to introduce these concepts, here's a proof in the same guise on lists. The proof rules for proving things about lists will be updated in the notes. I still need to make a small revision on that, but those notes should be live tonight. And the higher order functions, the best resource for that would be my lecture on Monday. And I can also link you to Prabhakar's Teach Yourself Racket notes, which will be an allowed resource during the exam as a reference for Racket. Are there any questions about that?
A question about the homework?
Right.
Can I ask those?
Is it specific about, is it like something specific about your solution? I mean, go ahead, ask the question unless it's...
No, this is actually more general, I hope.
Right.
This is PF3.
Yes.
Okay, so is this similar to the PF1 proof or?
Yes. So PF3 is, I will update the notes with a section about the rules of reasoning about lists. But the style, the structure of the proof will be exactly as PF1 and PF2. There's going to be one small difference in that in your recompute blocks, instead of giving names to every single rule or every single reduction in rackets, there's going to be a slightly more relaxed standard about justifying one step in a recompute block to the next. So you'd be allowed to do, if you looked at the equivalent racket code, several steps of rewrites to go from one term to another equal term. Roughly, if you were to draw what these functions did in AST form, then you'd be able to jump from one AST to the other AST, which in Racket, you don't have matching in the way that that code is written. And even if you did have matching, there's code that determines, oh, is the expression that I've been given an empty list or cons of something? And those checks, well, they take several steps of computation. And that's not what I want to show in the recompute blocks. So in the recompute blocks, you'll be allowed to skip steps in that way. And in the same way, you won't have to write justifications for naming the types of computations you did, so long as they're legal computations. But the standard for this and what I'm relaxing will be very carefully described in the notes for this. So before you start writing this, you should wait for me to post those notes.
Okay, I think that will be helpful.
Right.
And,
so I'm sorry that I haven't yet posted them. That should have been something that I did sooner.
Just a very quick question on PG4.
Yes.
Okay, so you give an example of some list, and I wasn't able to figure out what the symbol was after folder. It says define some list. Then it says folder plus, and then a symbol list. What is that?
Was it the first definition? Oh, that had arguments, or was it the definition that had lambdas? I gave two definitions in the problem statement.
It's the one before the lambda. Actually, they both have it.
Yeah. Oh,
it's
right.
a 0.
It's a 0?
Yes.
Thank you.
So one way to think about it is that a list of numbers generally looks like this. Let's say cons 1 onto cons 2. Let's say this is the list in question. So this would be list 1, 2. Then if you think about what foldr does to that, if you think about the function foldr,
Taras, she just couldn't see the
yes,
printed 0.
yep.
That was the question.
Yes, I was going on definitely on an off-topic tangent, but okay, to finish the off-topic tangents, foldr roughly replaces your original computation, your original lists, the conses with the plus, and the empty list with 0. So that position of foldr goes here. That is definitely not an answer to your question. That was me going on an off-topic rant. It's the symbol 0 is the correct answer.
Thank you.
So in summary, and of course, with a lot of you, I know that I'm going to be speaking with you on the weekend because it's very important that you catch up before the midterm. The midterm is supposed to force you to catch up on the material and also serve as a really good diagnostic guide for your understanding, and it'll force you to form the understanding that you need before the midterm comes along. And really, the most important thing about doing in preparation for the midterm, and this is why I said that, for example, seeing answers to PF1 and PG2, or seeing answers to all of the homework problems won't necessarily help you on the midterm if you just see the answer. Because I won't repeat the questions themselves. I'll take the reasoning skills that I thought were most important that you learned from these assignments, and I'll ask a completely new question, not a restatement of the homework problems. So your solutions for the homework will not literally be useful in the exam, but the same reasoning skills that applied there will apply directly to another problem. And so that's why it's important to go through the homework yourself and to think through the problem and think about what process did I use to think through the problem? And how can that process be applied to other problems? Maybe making slight variations of what these questions are. And now, if you're stuck and the midterm's coming up, this is when you contact me. In fact, you should contact me. And so I expect to be speaking with a lot of students. I haven't had a lot of students schedule time for me this weekend. If you're not caught up on the homework, spend time thinking about it and then ask me questions. And then we should set up a Zoom meeting. I've spent many hours speaking with students in Zoom meetings so far, and I expect to do many more hours this weekend. So now is the time where you get through all of this material. It's going to be hard, but the midterm starts at 8 p.m. on Monday. And during the midterm, I'm not going to be able to answer technical questions. If you think there's a problem with marmosets, or I mean, you can ask me questions, but if they're actually related to the contents or of the form I don't understand X, then all of those clarifications would be things that you would have had to have asked me before the start of the midterm. So 8 p.m. on Monday is the deadline for using me as a resource to develop a good understanding of problem solving and develop a good understanding of how you would go about solving problems similar to these homework problems. And okay, you'll soon get an email with, with several resources, and then shortly afterwards an email, maybe in 2 or 3 hours, with another link, to the notes, but I'll specifically tell you that now they've been updated with the proof rules for lists and an example written in the form that I would have wanted to with the proposition that I covered last Friday, I believe. Are there any more questions?
Taras, I just wanted to mention a couple of irrelevant musical points. One is that you've been pronouncing LACI as Locky because computation has a hard K, and that makes sense. But I was pronouncing it as Lossy because it sounds like a Philip Glass opera lyric of the type you've played for the students. The other musical note is that if you look in Lossy, there are epigrams, there are short quotations at the beginning of each chapter. Those are taken from the 2 songs that Taras played for you at the beginning of lecture today. That's all I wanted to say. It's really a tangent.
So, and again, having Prabhakar speak today was quite a treat, and I hope all of you enjoyed that. So it looks like we're out of time. Oh, wow. We are out of time is an understatement. I did not notice that. Okay, I expect to speak with at least half of you during the weekends. Again, I'm stressing that. Seriously, reach out to me for help during the weekend. Get caught up on the homework. This is one of the main points of having a midterm. Get caught up. Okay, have a good weekend. Have a weekend in which involves a lot of looking at these problems. And I'll see you on Monday.
Yep.
Thank you.
Have a nice day. I'm going to close the meeting now. And thank you, Prabhakar.